All right, I'd like to welcome everybody here to the symposium in honor of our friend and colleague, Devendra Lal. Many of you know Lal better than I have known him, but I think we've all known him for many, many years. People have come from all over the world, literally, to be here today. And we thank you for taking the trouble and being here and making the symposium a special event in Lal's honor. First of all, I think that rather than do it at the end, I'd like to acknowledge the people who put the most work into making this happen. And I think the person at the top of the list is Donna Stout, who you've seen running around trying to make everything organized despite the natural disorganization of the rest of us. And we need to thank also the Scripps Director's Office and the administration who has helped us put this together. We have a small organizing committee, a few of whom have done a lot, and among those are Doug McDougall and Jeff Gee, Kurt Marty, Tim Joel, Mark Thiemens, and to some extent me. Now, Lal served, I figured out, he served at Scripps under 5 directors and a number of interim directors. There are only 2 surviving former directors, one of whom is Tony Haymet, who sends his regrets because he's been called to a conference on the East Coast today, and he wanted people to know how deeply he felt about Lal as a tremendous human being and contributor to the institution in so many ways, which you'll hear about later. The other former director, living former director, is Charlie Kennel, who's here today, and Charlie will give a short presentation about Lal.
I just thought I'd recount an annual ritual that Devendra and I had together. And once a year, he would make an appointment at my office for 1 hour, exactly 1 hour. And he would spend the whole hour telling me about his most recent project, believing, in fact, that I could understand what he said. And he put me through my paces as he described whichever project he was working on. And at the end of the hour, he got up very politely and he thanked me. And he said he would be back the next year. And there was a hidden subtext that neither of us had to speak aloud. And that was that Devendra had been retired for quite a number of years. And the University of California has an option whereby they can recall emeritus faculty back to active duty, RTAD. And this requires a decision every year by the director. And what this would do would provide him with a very small fraction of the salary that he had received as a faculty member on the regular staff. He was, of course, as active as he had ever been, which was the point of it. But the other thing was that he didn't need the money, and we didn't need to give it to him. And in fact, I think he donated most of the money back to the university every day. But the subtext was that he loved Scripps, and he wanted a token of our love back to him, our connection with him, and I very freely gave it. And I believe that continued to the day he died. But he treated the director with respect, and the reason that he wanted to stay active at Scripps was entirely to pursue his research. It's quite a remarkable story. So later on, after Aruna died, Devendra decided to leave his entire substance to Scripps Institution of Oceanography. And we've endowed a Devendra Lal Fellowship, and Ian Long, I think, is here, is the first recipient, and there will be many more. And his memory will go on for a very long time. And so he gave both his soul and his substance, all of it, both, to Scripps. I'm just going to conclude. I'm going to not take much time. You can go on like this for a long time. But I'd like to recount to you the impression he made on a young person that I was working with, whom he met only for 3 occasions. And this was a colleague of mine from Cambridge, and we were trying to work we failed to successfully work a collaborative program between Cambridge and India and UCSD and Australia, and it fell of its own weight. But this was, while we were doing that, we were trying to make all sorts of international arrangements, and Sally Daltrey, who was a trained scientist, was very good at this. And later on, she came to visit us in La Jolla for about 3 weeks, and she asked if she could meet Lal. She'd heard of him. And so, and this was just a couple of years ago, and so I mentioned to her that this symposium was going to occur, and she immediately wrote back on what you see here, and I thought it was so touching that it would be a better closing than I could make to my talk. So I'll just read it. You can see it too. On my global travels in the cause of science diplomacy, which is what she does, I meet many bright stars. Very occasionally some shine brighter than others, and Devendra Lal remains one of these. My memory of my first meeting with Lal shines as bright as a La Jolla morning, platinum blue sky and ocean, a fresh day filled with great promise of new discovery. Lal invited me to explore his laboratory with the love and attention of a meticulous curator and the keen curiosity of a true discoverer at his work. How many of you recognize those qualities? A man who dedicated his life on earth to the pursuit of scientific truth and the joy of sharing that knowledge to inspire others. All this from 3 meetings in La Jolla. And then here's the punchline. He told me his greatest fear, waking up one day with no new good ideas. Well, Scripps now will wake up every day with fewer good ideas because Lal is not here.
It seemed appropriate to start this program with the earliest history of Lal here, as we called him. In the summer of 1977, Harmon Craig had invited my husband, Jim Arnold, to SIO to work on a joint project. So we spent the summer here. Towards the end of that summer, Roger Revelle invited my husband, Jim, to come back as next year as part of the developing the new campus at the UCS, actually at San Diego, because it wasn't decided where it was going to be yet. Well, Jim, we returned to Princeton, Jim thinking this over. Shortly after, we welcomed the Honda family from Japan to postdoc with my husband. We spent the year. During the fall of that year, there was a public announcement that Harold Urey was coming to SIO from Chicago the next year. Well, my husband thought about that for about a week or so, I think. I don't remember exactly how long, but he gave notice at Princeton that he was not returning at the end of that academic year. And he also, of course, notified Roger what he had in mind. So we had also welcomed that fall the Honda family. They to postdoc with Jim. At the end of that year, we returned to SIO, and shortly in October. In December, the Lals came. I hope this is working because I'm not touching it. I don't dare. So we settled in T39, which is still standing, I believe, And the Uris were in T29, which I guess is now the Martin House. And and the Moss's Honda settled somewhere in the area. In December, Lal and Aruna arrived, and they were settled in one of the other tea houses. I believe that house no longer stands. And this began the adventures of Arnold Honda Lal, which no longer exists now, because, as you might have heard, Masa Honda passed away in, I think it was February of this year, in Japan. So Lal was very interested in the children. And basically, for example, on a long road trip, Lal knew that he would be pestered by Ken, especially the youngest, for jokes. So he came prepared. He kept promising the donkey story later. But right now, he would tell a different donkey story. Over several days, out came donkey story, and then donkey story, and then donkey story. And finally, the donkey story. In this, and as in so many other ways, the boys came to see Aruna and Lal as their aunt and uncle, which actually it sort of seemed like, because the three of us did many things together. We picnicked, and we sightsaw. We went to camped in the desert, at Brimbrago Springs especially. It was a really great relationship. Aruna learned to make pizza early on, and some other non-Indian dishes, of course. We all exchanged meals. We went on picnics. The Arnolds took 2 sabbaticals, 6 months in '62, and then a year in '72. We spent most of the time in India with Lal, but we stopped in Japan on the way home to see the Hondas. We saw a lot of India, from Kashmir to the southern point of India, not all at the same time. Of course, Jim managed to entertain the boys when they were there. The first year, the second year, two of the boys were in high school still. So we stayed in Bombay until the end of the Christmas vacation, even though Lal had moved up to Ahmedabad a couple of months before. In the following year, in the spring, as soon as all the boys got to Ahmedabad, they went to school. That is, the 2 boys went to school. Bob studied guitar, and no, not guitar. Yes. You're right. Yes, guitar and right, he was guitar already. And we had, the rest of the year was really great. When Lal was appointed to BRL, we couldn't stay in Bombay, so as I said, we went up. Lal kept coming here on a regular basis, and every time there were get-togethers. When the boys went away to college and so forth, otherwise live elsewhere, whenever they came home, there was always a visit with Lal. So it was, he was part of us, sort of like an aunt and uncle for the boys. And of course, when Lal retired here, thank you. When Lal retired here, it was easier to spend time with him. And again, when the boys were in town, we went to eat with Lal, one way or another. Jim passed in January last year. Honda passed in about February this year. And Honda passed in about February. Lal had passed in November, I think it was. and should say here somewhere. So it was something to remember. I look back on with a lot of love and sad feelings too now, but I think they all left this place a better place, and I do hope, and I understand that they did help the research a lot. Thank you.
The next speaker is, I think, the person in the room I've known the longest, because I had the misfortune to take mineralogy from Jerry Wasserberg at Caltech when I was an undergrad. And he hasn't changed. And so I think we all know Jerry, and we welcome him here to Scripps. Jerry, you're on.
We're here to celebrate Devendra Lal, and I tried to do enough facts together that people had a few things as best I could ascertain them, and also to put things in a historical perspective, which we tend always to lose in every possible way. He was born on the 14th of February 1929, died December 1st, 2012. He had 7 brothers and 4 sisters, which might explain why the Lals never had any children. Now, he was 18 years old when India achieved independence from British rule. So you have to put that in a, thank you very much, ma'am. I made good for the other speakers too. And that took place through the inspiring leadership of Mahatma Gandhi on 1947. Some of you may be old enough to remember this. And this independence movement was based on nonviolent resistance and civil disobedience, which seemed to be quite successful, but it ended in the formation of 2 sovereign states, India and Pakistan, with great violence. And Gandhi was then assassinated in 1948, which Lal was not very old in, by extremist Hindu nationalists. Lal graduated from the Benares Hindu University in Varanasi in 1949, went to study at Bombay at the Tata under the supervision of Bernard Peters, which I will go to. And Peters had joined the Tata in 1950 when Lal arrived. Now, to hit the next button, what do I do?
Don't ask Ray. Yeah, it'll do it.
Fine, okay. Now, a little bit about the Tata Institute. It was a non-Gandhiist enterprise. It was a desire to bring India into new and high technology things and not back to the farm, weaving simple things, by J.R.D. Tata, who was chairman of the Tata Group and had the resources and wisdom to found it. And the first director was Homi Bhabha, who then found this fellow Bernard Peters, we'll talk about. And Lal and Sri Kantan and Vijayaraghavan were involved in the very earliest years as junior people. In 1972, he made a major career move. He moved to the Physical Research Laboratory, the PRL, at Ahmedabad as its director, and he initiated new programs in earth and planetary sciences and was responsible for the Infrared Astronomical Observatory, which broadened the PRL's functions consistently. Now, he relinquished the position of director in 1983 at the age of 54, and then he split his time, as you now very well know, between the PRL and Scripps, where he has served as a full-time professor until his demise. Now, he did not enjoy administration. Dealing with the Indian servants or civil servants and the strikes that he had to put up with drove him up the walls, and he was not about to go into administration. He found he liked science. Now, the Tata, am I going the wrong direction? No, I'm going the wrong way. This is a picture of Lal when I about first met him. A long time ago, he looks very serious. Oh, I hit the wrong button, that's the problem. Now, the one thing I know about Lal had to do with my first Lal experience, which was in 1959 in La Jolla at the Craig's house. With Harmon and Valerie, we were staying there with our kids. And the Lals had just come. And he liked puzzles, and that's the theme of what I want to talk about, are the puzzles. He came in the house with Aruna, and he's a pretty tall guy compared to shrimp like me, and he says to me, "You're an experimental physicist." I said, "Yes." He said, "You must like puzzles." I said, "Yeah, I like puzzles." "Oh, come with me." So we sit down on the floor, and he reaches in his pocket, and he begins to take out little pieces of metal. They were not these fancy puzzles which I got off the web, because I don't do that for a living, but they were things which are obviously made by a blacksmith. And he said, "Now, you must take them apart. It is subtle." I said, "Okay, I'll try that." So we sit down on the floor, and I'm starting to take this stuff apart. And then all of a sudden, his voice raises to almost a shriek. He said, "No, no, you must not do that. You do not bend them. You take them apart subtly." And then he went zip, zip, and the thing was apart. So he gave me another one, which I tried for a while and decided I would give up. And that was the story of my first meeting with Lal, and it was a delight. And the puzzles, which he always sought for his whole life, were the key to his existence and the vitality. Now, I have to bring you back to 1950, because this leads into Bernard Peters. If you look at the situation in the United States, US&A in 1950, there was a character by the name of Senator Joe McCarthy who was nothing but trouble and had really evil effects on the nation. There was a cartoonist by the name of Walt Kelly, who's one of my heroes, and this is a picture of Pogo sowing seeds of dissent, disorder, confusion, wisdom, or possibly food. And he was the protagonist in Kelly's wonderful political but cartoons which were good for kids and had Latin puns in them, so it was very difficult. And amongst the things that he did was take on Senator Joe McCarthy. And here is Senator Joe McCarthy is drawn from Carol's Alice's Adventures in Wonderland to judging who stole the tarts. And this book, the moon was not visible then in 1950 as anything. And this political fervor, which brought about searching for communists under every bed, and anybody that he imagined was a communist or could accuse of it, led Bernard Peters to leave the United States, although he had fled Nazi Germany to come to the United States. And while it was clear he was not going to put in a concentration camp, he was having a lot of trouble. And Homi Bhabha invited him to the Tata. And that then made all the difference in the world and everything you see. And this is the obit written by Dayton, Devendra Lal, Niels Lund, Schnupfer, and Phil Morrison. And the effect he had as an American professor in 1950 in India, which had just then been made independent, was a university professor who actually went in the field, did work, and did all sorts of vital things. And the students he was flying cosmic ray balloons, developing emulsions, going up into the high Kashmir snows to get samples of cosmic ray products there. And the graduate students at the Tata, who were then Lal and a few other people, became so devoted to this professor who worked harder than they did and try anything he could understand and explain anything, and he was their friend. And that was a new game, and that established a level and a quality of scholarship and intensity in India, which lives well today. Now, the masterwork that I think one can attribute to Lal is Lal and Peterson in '67. Cosmic rays produced radioactivity on the Earth in Handbuch der Physik. And this masterwork is also the outline of the story of Lal's life, and is also the current status of the field today, which is an enormous compliment. Now, this is from the first chapter, protons and X particles, since then you didn't know what the other particles were, and heavier atoms come bombarding in, and the issues were nuclear transformations within the Earth's atmosphere and the outermost layers of the Earth, including the surface, where nuclear reactions down to the depth of 2 meters. And we are here in absolutely a current 19 excuse me, I'm in the wrong century, a 2013 status of the activity in the field. And with the oceans, with the transport problems, I just take them as symbols, not to read, of the intensity and depth of an article of such profundity that if the people who are working in the field today understood what was written there, they probably would quit. And here are the transport processes clearly and unambiguously laid out: rock, soil, ocean, mixing, and all the transport issues, plus the cosmic ray production as a function of latitude. Then, more recently, in 1988, he wrote, with the advent of accelerator mass spectrometry, in situ produce cosmogenic isotopes in terrestrial rocks and their implications. And these two are not research documents, except the first one was, but these are essentially tell you where you are and where you should go. Now, this is the only picture I have of Aruna dressed in her glorious sari, and Lal and my wife, and I don't know who that is. My wife now has a collection of saris, which Aruna and Devendra gave them at some festive occasion at Caltech. He didn't always wear a tie, and that was not the typical way they were attired, but that was the way I like to fondly remember them. Now, he would occasionally come and visit us, in particular when he arrived, because he was a devout vegetarian, we had problems with feeding him. Well, I could make scrambled eggs, and my wife could do some more subtle things. But Lal arrived at the house with a suitcase, a big suitcase, full of Indian food. This is what's left after many years, and I don't know what to do with it, but we saved that. So in the house, there are shelves in the closet where the Lal, they were not memorial, they were just Lal shelves, where when he would return, he would have something to cook with. And you can look at some of these things. The most important thing to look at is this over here. It says habanero chilies. Now, I wore this suit. This suit is 40 years old, and broker said I can't button the vest, but well, I'll have you have a three-piece suit. And in his pocket, these are hearing aid batteries. He did not have that. He used to have a little plastic pouch with habanero powders in it. And when you weren't supposed to be looking, he would take it and put it on the food so he could make it tolerable to eat. Now, this spicy business is fine. This is not Aruna behind here. This is Parvati, a beautiful bronze, the consort of Vishnu, I believe. Now, so there are these foods he had, and he was a very strict vegetarian. The only time I ever saw him completely go nonlinear was we were at a meeting and we ordered breakfast. And I had my normal light breakfast, and he ordered scrambled eggs. And he said, I am a vegetarian. Well, he got his scrambled eggs, and all of a sudden he looks in the plate and he sees a little piece of bacon in it. When he came back from orbit, the waiter was, of course, singed beyond recognition. And he said, well, I'll just take it away. He missed the point of this thing. So the breakfast was delayed, but that was an interesting experience. It's one of the times I really saw him lose his temper. Now, mentoring is a thing that he was excellent at, but it also relates to the Peter story I told you about. And this article is from an article by Jeremy Denk in a recent New Yorker called Every Good Boy Does Fine, which is some instructional thing for a piano. And this is a description of mentoring young people by a teacher who then becomes a professional and remembers what professional advice is. And he said the following thing: in this complicated situation, a teacher must walk a thin line, destroying complacency without destroying confidence. And that is, of course, the game. And that Lal exceeded at that. And the theorem that follows is that great mentors have great students who are great mentors. And so was Lal. Now, I want to make a funny thing about grace and graciousness, kindness and understanding. When Harmon Bushnell Craig died, was for many years a good friend of Lal's and Devendra's and Aruna's. Lal spoke at the memorial service. He wore a three-piece suit, which is why I'm wearing this tonight. And when Valerie died, he went to the home to visit with the daughters and extend his condolences. In all of these comments, he never said a single thing but supportive and kind words. This was in spite of the fact that he and Aruna had suffered one of Harmon's not infrequent and violent attacks of meanness and nastiness, which attacked him severely during the time when Aruna was dying in particular, with an improperly formed lawsuit at the University of California at San Diego. The fact that he could respond this way was a testimony of such greatness and generosity, such gracefulness and understanding of the human endeavor, that is a respectful statement, and I must make it here today. Now, he liked the puzzles, and the puzzles were a mixture. They were a mixture of actually trying to understand nature, and I'll cite clever things like carbon-14 in ice. Yes, carbon-14 in ice, trapped atmosphere. Well, but also you have it produced in the ice. And he would then take this puzzle apart in nature, which he just loved to do, and did things like using iron-55 and silicon-32 rain out in the ocean to get rates. There's a long list, and you will all be talking about that. Beryllium-10 was his great heroic thing. And I was once at a party here where he was given a wonderful piece of frosted cake or something like that. It said beryllium-10, I got aluminum-26. So the puzzles he had were the puzzles in nature plus the desire to play with equipment and make things go. And that was always an enormous thing. The covering, the covering photo of Lal in the lab is the one with Lal with his real puzzles. The puzzles he wanted was to understand something of nature. The other puzzle was he wanted to make the machines work and by some subtle things get gadgets which should have been buried long ago to function and give him wonderful and important data. And this is a picture that came from Kuni Nishizumi of Masa, Devendra, and Jim Arnold, which Louise showed earlier. This was taken by Nishizumi, but he was so struck by the death of these three heroes of his, he could not let himself come. I thank you.
Thank you, Jerry. That was a most moving tribute to Lal that has a quality I think we all recognize. We're shifting into we had a little difficulty making categories out of today's agenda because Lal did so many things that it was difficult to take any two of them and put them into a category. So I hope you'll excuse where we have a slight mismatch, but we tried. So now we're shifting to the topic of cosmic ray products and applications, and the first speaker is Bob Reedy from Planetary Science Institute with the title, Over 5 Decades of Studying and Modeling the Products Made by Cosmic Rays.
Lal was a giant in the field. Of course, he was a big person, but he also, usually he came into the room, you knew he was coming in. Some people referred to him as the big blast. He often came in that way. But, and of course, we collaborated on a bunch of things, and of course, often I'd be sitting at home very quiet, and this female voice, "Hi, Bob, Avruna here. Lal wants to talk to you." Now, if you were lucky, he just wanted, "I like that paper you did. Please send me 2 reprints, one for the house and one for the office." And so we always had to mail Lal 2 reprints. So, so that was the old days. I don't know who had to clean out, but he must have had a humongous file. Yes. So anyway, so this is a good picture. Especially I like it because it does have a runa in it. Let's see if I can do this without zapping myself. So there's a runa. And I got to know Lal when I, as young postdoc fresh out of graduate school, joined Jim Arnold to work on Apollo lunar samples and then the Apollo Gamma ray experiment. So this is the team Jim had assembled, and some of the old timers came back, Lal, Masahanda, Julian Shalosky. We got a whole bunch of graduate students and postdocs, and it was a superb team. And of course, we had 11 people on the Apollo 11 paper, and we decided that's kind of complicated. Let's make an acronym. And it was tricky because there were only 2 vowels. And Jim said his biggest contribution to Shreldelf was the letter A. So this was quite a good crew, and of course with Aruna there, that was, things. So see if I can get this to work. Okay. Now, soon after I arrived, the Apollo rocks arrived, samples, and the first was rock 10,017. We didn't know what the top was. We had hints. Sorry for the bad slide, it's a thing. So what do? Do we wait, we go, or we got a Suma talk, and then Lal pops up with this handmade thing. Your mission, Jim, should you decide to accept it, is to determine the surface of rock 17, which we didn't know. This rock will self-destruct in 78 days, which was the half-life of cobalt-56, the isotope we really wanted to measure. So this is Lal's input to our thing, real nice drawing, this was, and of course Jim's laughing his head off. So it was a good team. In fact, I had to sort of think, what had I done with Lal? So I went back through my list of reprints. We did Shreldelf, and then sort of things quiet, and then we decided we needed a good review article. Lal liked review articles, as Jerry was noted, and this was one that we did on the cosmic ray record. Lal covered nuclear tracks. We had a long article in the Journal of Science, and then even a longer one in Annual Reviews. But then, of course, one of the phone calls later, sitting home, Lal decided he was going to do some measurements of beryllium-10 in samples that had a lot of boron, but he didn't know if a thermal neutron on boron would make beryllium-10. So he called me up, Bob, can I send you a sample and please irradiate it at the reactor? And so, okay, so he sent me a sample. I irradiated it at the Los Alamos reactor, sent it to Kuni Nishizumi, who did the chemistry, sent it to the group in Zurich who did the AMS, and we wrote up this paper. It wound up being in nuclear physics. It was a cross-section paper. And then Lal also in the early 80s got intrigued with solar protons. Goswami probably can know more about this because he was somehow got conscripted, invited to sort of lead the effort. So we did quite a bit of work with Bob McGuire from NASA Goddard Space Flight Center. So this was a fairly big effort. So Lal was quite active on that one. Then, he also was already thinking in the 80s about cosmogenic nuclides in situ. So we were talking, he was big on pushing for simulations. So we did some at the Los Alamos Meson Physics Facility. We did energetic particles, and then we also did muons, quite a bit. Lal knew muons were going to be very important. And we knew nothing. In fact, when we first did some of these measurements, we were expecting muons, negative muon can be captured and go in orbit around a nucleus. It's basically a heavy electron, but it orbits generally for heavier atoms inside the nucleus. And it can induce nuclear reactions, but the typical reaction is usually only a few particles out. So Lal was predicting if you put quartz in a stopped muon beam, you'd only make aluminum-26 and almost no beryllium-10. Well, we were very surprised when we did find it, because I had agreed with Lal. You wouldn't make it, but we did. So Lal always wanted to be certain that we had things. Simulations, good basic nuclear physics, nuclear data were very important for all these projects he wanted. He wanted to do it on a solid physics basis. So some of the very earlier work dates back to, as I say, almost 5 decades of measuring, modeling the production of cosmogenic nuclides. Lal wanted to know, can you tell me what should I expect? So he always wanted things. Of course, he had done some in the early days. Some of the very early work just used, someone had bombarded 10 tons of some target and then made the measurements and then tried to unfold it from there. But Lal didn't like that approach. He was more interested in using particle fluxes and cross sections. Lal did work on and off on particle fluxes. In fact, when I started doing some of the Monte Carlo work, what was the best analytical formula for galactic cosmic rays was one that Lal had done with Dr. Costanoli back 30 years ago. So, yeah, Lal was quite involved with doing some of these things, and then many people went to Monte Carlo, which is now the Tectonic. We did mainly extraterrestrial matter, but now we're doing in situ, which we'll hear more from John Stone and some others later. But also I had to look into muons. So I did those muon irradiations because he was intrigued by those. He thought they might be very important. So this is an old picture, again, back from the old days, Farmer Goel, Lal, Jim, the gang. So these are more reminiscents now. You know, this is the gang that sort of got started in modeling production rates of cosmogenic nuclides. So these helped me get going. When I joined Jim's group in '69, Lal was a great help in getting started. He sort of basically handed me this Arnold Honda Lal model from '61 and said, this is a good start. Why don't you expand it into doing things for the lunar samples, which, if Jerry remembers, we got the samples in mid-September, and by early January, we had to be in Houston telling the bottom line that we understood everything. So we were working hard, and we decided we needed a model, so with Lal's help, I quickly got some sort of crude primitive model to try to explain what we were seeing, both solar and galactic cosmic rays, so worked pretty hard on that. So Lal was a big help in getting me going. So as they say, he really was quite interested in cross-sections. In fact, one of the earlier works on trying to estimate cross-sections. See, the early days, the cosmogenic nuclides, many of the long ones were not being measured. They were just so long a half-life that the activity, you know, for example, if beryllium-10 has a weak beta particle, he did develop a counter that could measure beryllium-10, but you needed a lot of it. You know, as Jim Arnold said that, okay, he would help with the Apollo program, but it cost NASA a kilogram of lunar samples. But you needed a lot of that in the Apollo days because the low-level counting, you needed 100 grams of material to produce enough to get a count rate in a simple counter. Nowadays, you can do accelerator mass spectrometry. You can count 1 million atoms with no problem. But if you had beryllium-10, 1 million atoms has 1 decay per year. You're never going to count that. So Lal was fascinated when accelerator mass spectrometry pushed this business. And we were able to make cross-sections, a lot of new work. But Lal also was quite intrigued with just estimating cross-section. He did a lot of work back in 1967. He was interested in cosmic dust and what it did when it went into the sediments. And he went through and compiled a whole bunch of cross-sections and used analogous reactions to identify it. But you know, more recently, Lal was very happy to see we had good measured cross-sections, and he was always pushing for that. He said, no, but neutrons are important. We got to do more neutron measurements. So, okay, well, we've been doing that. In fact, Kuni Nishizumi is still doing a lot of them, which we need. Well, these are a few pictures. There's a meeting from a Meteoritical Society meeting with Goswami, who will talk later about it. These are practically, you know, I went through a lot of the work over the last 30 years. It always is Goswami, Lal, and Lal and Goswami seems to be a very common number on all of these. So, I mean, we'll certainly hear some very interesting things from Dr. Goswami. Another good colleague who also will talk is Tim Zhao. You know, you were honored to be picked by Lal as a colleague. It was a sign you were a good scientist. He didn't put up with mediocre scientists. Lal could not tolerate mediocrity. In fact, it was very hard for him to keep students. I don't know, maybe 1 or 2 actually survived Lal. He would have students, and their half-life was probably measured in months. I mean, he demanded perfection, and these guys weren't quite ready for it, you know, and it took an exceptional person to get through it. But if you were in the inside, as I say, you were blessed to be friends. Of course, it also meant you got calls from Lal all the time asking for this and that and the other thing. So, you know, so it was always quite an interesting, you know, thing, you know. But it was great to work with Lal, you know. So, you know, and Tim, Zhao, and Lal always liked carbon-14, so he and Tim did a lot of work on that, and you will hear about that later. Now, this is just a nice picture of Lal. I like his expression. This was at Candace Cole's house before our Jim Arnold lecture, Florence Kirshner. He's enjoying himself. He enjoyed life. So he was having a great time there. But I want to close with one that I took at that same time at a gym lecture. And he's talking to Joe. And obviously something interesting, because the look on his face is, let me think about it. Now, I think that's what he's thinking, isn't he, Jerry? Would you say? Well, I won't argue. That's probably where he was. Okay, well, I'm going to close here because I don't, I could go on, but I think I'll let people, because we need to get back on schedule. All right.
Thank you, Bob. Okay, the next speaker is Mark Thiemens and Subrata Chakraborty. I'm not sure who's presenting what in what order. You're going to tag team. I just want to interject that Lal's high standards with regard to students live on. He has, as Charlie Kennel mentioned, endowed a student fellowship here, and he wrote down the standards for that position, and they are so stringent that that you should honor anyone who has that position.
I'd written down a few things to say. Now that I've listened to the first two speakers, I've left them on my seat. So I'm going to do this randomly, but possibly chronologically. 20 years old, University of Miami, I'm an undergraduate. I'd taken all the courses in physics and chemistry, so I needed to take more science courses. Biology hadn't been invented yet. Engineering was a stigma to your social life. So I looked through the catalog, and there's a course in geology. I said, that's great. I've collected minerals since I've been 7 years old. I love studying them. This is perfect. I'll take it. I took it. It was transformative. Best course I ever took in my life. To this day, the man who taught the course was a hero. And he taught a big section on isotopes, stable isotopes and radioactive isotopes. I'd just taken nuclear physics. It was perfect. And I thought, why didn't they tell me this? You could do all this. So I would go to the University of Miami Marine Lab, now known as Rosenstiel, and I started reading in the literature on my own, Earth and Planetary Sciences, Geochemical. And then after a while, I said, I start thinking, I have an idea. So I go and see if I've looked it up. It's been done. So I think a little bit more. Go back. It's been done. So after about 3 months of this, same damn people. I mean, it was the same people. It was Lal, Craig, and Wasserberg. And so finally, out of exasperation, I went to the professor. So Professor Emiliani, that was the guy who taught the course. Cesare says, I said, I'm sick of it. These guys have done all this stuff. I said, do you know these guys? He said, yes. And I said, do you know Lal, Wasserberg, and Craig? What do you think? He says, Lal is a very great man. And that was all. So he went. Now, I guess it's a problem when you're classmates with someone, is that they pick on each other. And so I came to here as my first real job in 1980, and my office was next to Hans Seuss and Jim Arnold and Gunter Lugmeyer and Kurt Marty. And Lal would come up all the time, once or twice a week, and he discovered that I was there. And he would come in and talk. It was great. It was just, he was just thinking about the in situ radioactive production of isotopes and how to measure them. We talked about, I just come from Chicago and measured cosmic ray effects in lunar material, so it was perfect. And he talked about all those stupid papers that I read and thought I had found something and hadn't, and told me the background on it. So it was wonderful. We got to know a lot. And like all of you, I experienced the 11 o'clock Sunday night telephone ringing. I'm not a late night person. I'm an early morning person. So 11 o'clock night is not my sweet spot. Mark, you must tell me, has anyone measured calcium isotopes and calcium carbonate? Is a thermometer for the, you must tell me now. I said, I'm sleepy. No, I must go. I won't let you go until you tell me. I said, well, look, the effects are probably really low and it's hard to measure. And so, and he said, oh, okay, we will come talk some more. So it was great over the years to talk quite a bit. I learned a lot from him in all those conversations. You know, they go from everything from ice ages to the moon to solar systems to everything else. Now, in the course of that, Lal had a way of doing what I guess you could call it the left-handed compliment. It goes this way. He came to me one day. He said, Mark, I have a very great student at PRL, one of the best students we've ever had at PRL. The problem is this fellow Bhattacharya is too nice, and he's not mean enough. I think he should work with you. So Bhatta did, and you'll meet the son of Bhatta who's going to take the other 7.5 minutes, and he'll probably give you a different perspective on this. Now, in the course of working with Lal, and some of you are going to know at least one half of this side of Lal, and some of you will know the other half. I've seen both. I don't know what to call this. I'll call this the Lal phase transition. The Lal phase transition goes like this. I came here as 29, 30 years old. And I would go to dinner sometimes over at the Seuss's house. And Seuss and Harmon Craig would be there, and Jim, and a number of people. And we would be sitting around the table, and these were this was the all-star team and me. And Lal, and you saw that expression in the last slide. When Lal would frown, he had a frown that went to his knees. The smile went to the moon, and the frown went to his knees. And sometimes he would shake his head and say, there are just no smart people today. The young people are just really stupid. And they don't have any ideas anymore. And being the young person in a room, I didn't know what to make of this. And it was never a happy moment. I say, well, maybe I'm using the wrong soap or something. I don't know. But at some point in the life, then I would be sitting at dinner with Lal when I'd gone through the phase transition. He says, Mark, there just are no smart people today. They have no ideas. And so all it was as he was, and you just heard it from Bob, he just expected excellence and a never-ending flow of ideas, and they expected them to be like him, and that's pretty hard to do. So the last thing is you learn things from people. I learned a lot of science from Lal, and you're going to hear the science all morning and all afternoon, and you'll probably hit the tip of the iceberg, as the saying goes. But sometimes you learn something that's important, and this is what I learned. I was sitting at dinner at someone's house again. Lal was sitting next to me. And Lal was messing around in his pocket. I looked down, and he pulled out a plastic bag. I looked down, and my wife was sitting across the table from me. And she looked at me, and this is, if you don't speak Persian, that means, what the hell's he got? And so what he had was chili peppers. That's what he said. He took chili peppers. And so I've adopted that. And so one of the things that I learned from Lal is that when you grow up and you don't, with liking spicy food, it's never spicy enough. So you always carry chili peppers with you. Now, the one last thing I have to say, Lal is really good at getting you to do things for him. I mean, he was, maybe the only one who was worse or better was Hans Seuss. And they had completely different tactics. Seuss would whine enough that until you would eventually give in, and give him whatever it was just so he would stop. But Lal had a special way of doing it that made you feel like you should do it, but you knew somehow it was wrong. I was at a conference in England, Cambridge ICOG conference or something, and the day before it left, Lal said, "Oh, Mark, you must be going back to La Jolla tomorrow, aren't you?" I said, and I knew this was not going to go a good way. I said, "Yes, why?" "I would like you to take a brown paper bag for me back to La Jolla." I said, "What is it?" He said, "Just some things I need back home." So he came back with a tightly wrapped up big brown paper bag, about 3/4 of the size of my damn suitcase. And so I said, "What is it?" He says, "Things for my lab." So I said, "All right." So I went to the airport. You go to the airport. "Well, do you have any bags given to you by strange people?" I said, "Well, define strange." So, "Oh, no, of course not, of course not." "Okay, fine." So on the way back, getting ready to line up, filling out my declaration form, "Are you carrying any seeds, agricultural products, this and that?" And I said, "Well, I filled it out, no." And then I was waiting for my bag to come to carousels in Los Angeles International Airport. Out comes my suitcase. It's been opened. Damn. But the brown paper bag's gone. And the brown paper bag appears just after it, spewing out seeds, agricultural products, and all the things that I just said. And you saw in Jerry Wasserberg's picture, I was the guy carrying back all that stuff because he brought it back from India. So I thought about it. I said, well, he probably didn't know. And then I realized, of course he knew. That's why he gave it to me. And then I thought a little harder. And I thought, well, why did he give it to me? Why didn't he give it to Miriam Kastner? Her office is right next to him. And I think he probably realized that I'm the youngest. I'm probably expendable. And so that's sort of a collection of science and reminiscences in my 7.5 minutes. Lal, I appreciate this, but wherever you are, man, I haven't forgotten Los Angeles International Airport.
It's an honor to be here and talking about Professor Lal and celebrating his life. My account will be more recent, like last 1.5 years, or so, decades or so. So what I did, I wrote a piece in his memory, and I will read that out. One fine, mild winter morning in the western city of India, a young graduate student went to the research laboratory, PRL, where he is only a 4-month-old veteran and still wondering, what's the research all about? It was a usual day for him. However, he noticed that there was a latent busyness in the environment of the laboratory, a kind of busyness which cannot be seen but can be felt. This guy, who was quiet and shy-kind at the time, could not help asking one of the fellow scientists of the laboratory out of curiosity, "Is there anything special today?" With a big smile, the scientist replied, "Don't you know that Lal is coming?" Without thinking, the guy asked, "Who is Lal?" And almost immediately he felt that he did a blunder, as the scientist's face hardened. Yes, it's true. Professor Lal had a stature of God in PRL. In India, there are 33 million gods. This young guy grew up listening to the stories of God like Krishna. While he was in college and university, he came to know about some of the gods of modern science, like Einstein. That day, he was ashamed of himself that he didn't know about Professor Lal, a science god from his own land. A very same day, Professor Lal arrived at PRL. Few of the fellow professors and scientists escorted him to the elevator, and this guy looked at him from a distance with a pounding heart. It was needless to say that Professor Lal's gracious appearance mesmerized him. During his month-long stay in PRL, this guy thought to meet him and talk to him, but never had the courage to do so. Even he read his paper, which he got from one of his fellow scientists, Hard Rock Cosmic Ray Archaeology. He read that paper several times, did some math by himself, wrote down few questions, but he never could manage to accumulate enough courage to meet him. However, the whole episode left a big impact on him. During mid to late 90s, when almost every physics graduate in India wanted to do theoretical particle physics or string theory, this guy was no different. He wanted to do the same, but all that changed after reading his cosmic ray paper. Reading is not the appropriate word here. He, in fact, swallowed the paper with an urgency of an exam, with the hope of getting some attention. After all, what remained within this guy is the knowledge of cosmic ray radionuclides and interaction of cosmic rays with rocks. His views changed. The rock, which was once just a rock to him, got some life in his mind. He got hooked to the world of cosmochemistry. By now, I guess you may know who is this guy. This is me, and I'm still following the whispers of the cosmic rocks. I'm lucky. I landed in San Diego as a postdoc, got a chance to see the human being behind the shadow of God. His flattering words melted my young heart soon after, and quickly we became friends. I sometimes wonder how that was possible. He had a huge personality, and that was a big barrier for many to be his friend. I found a lonely soul in him. He wanted someone to listen to him. I just came to this country at the time, didn't have any friends, no family, no car. In that situation, his company was a relief. It was enlightening to be with a person who lives in science, talks science, and dreams science. One of the Indian saints, Sri Ramakrishna, famously told in Bengali, "Jatodin bachi totodin shiki," meaning, as many days I live, that many days I learn. It's true for him in cent person level. I observed that how curious he was to learn new things. I was moved. Once we went to watch an IMAX movie at Reuben H. Flitt Science Center in Balboa Park. We were standing at the middle of a long queue. There was an old lady in front of us asking Lal within a pastime conversation, "How many grandchildren do you have?" Thinking I'm his grandson. Then he replied, "Quite a few." Then he started describing me how great I am, portraying himself as a proud grandfather. That was very embarrassing, but that reminded me of my own grandfather, who was equally proud of me. That was touchy. We spent some quality time together. At times, he was emotional, unlike his personality, reviewing his own life and own decision, giving an account of things he should not have done. I heard a tone of regret in his voice. That was a different Lal. It was not that we had a smooth acquaintance ever. There were waves, ups and downs. I enjoyed his indulgence to break through the cloud of his personality. I guess he enjoyed that too, because he seldom had the opportunity when people intensely argue with him. It's not the usual argument about science ideas, but anything other than that. One of the favorite topics we argued over and over is the work attitude of our generation. We argued on that topic even when we met for the last time in October of 2012. His usual complaint was the present generation don't kill themselves for doing science, and without that one cannot reach to the bottom of it. I severely disagreed with his view without disagreeing that devotion is important. My regret was that I was not able to convince him that the basic physical principle of science has not changed, only change that has happened in the way we are doing it because of the advancement of the technology. This change will continue as this is an eternal process. Today, I want to assure him that the science is still in good hands. Many of you may know his attachment with Hindi music. I'm not sure that's the reason of ending the symposium with Hindi music. I was quite surprised when I came to know about his hobby. One may wonder, Professor Lal and hobby, those two doesn't go together. Yes, he had a peculiar one. He used to buy audio cassettes of Hindi movie songs, even in the era of CDs. Then he used to create his own song compilation in another cassette. The task was not as simple as a few mouse clicks of modern digital era audio tracks. With analog audios, it used to take a lot of time, extra effort, and patience. One day, he bought me a bag full of cassette as a present. The cassette he discarded after compilation. I accepted that gift. I never could match up this side of Professor Lal with the one we are all familiar with. May his soul rest in peace. Thank you.
So, the next speaker is Kathy Constable, a geophysicist, whose interactions with Lal come from the influence of Earth's magnetic field on cosmic rays, which was a surprise to me. It was a connection I didn't know Lal had. Kathy is also the interim director here at SIO.
Thank you, Ray. Yes, my interactions with Lal have occurred on a much shorter timescale, I think, than most of the people you've heard so far. One thing, since I came here in 1983 as a graduate student, and at the time, I didn't know it, but I was working for Lal. And the reason, of course, is because my interest is in geomagnetism, and he knew that the magnetic field was an important part of everything that he was doing, and that people needed to understand it better. But I didn't actually, I think, interact with Lal until probably around the time I became a professor here, which was in 1991. So I have to agree with Jerry that really the paper that is of enormous influence that Lal wrote is this cosmic ray-produced radioactivity on the Earth. And I also have to agree with his conclusion that we're still working on everything in this paper. And so what I thought I would do today is tell you a little bit about how the geomagnetic community has been working on what Lal told us to do back in 1967. So a little bit about the sources of cosmic rays. He was measuring them a long time ago, and now we're still measuring them. And we know that they come primarily from supernovae. Their galactic sources are supernovae, neutron stars, and black holes. And these are a couple of the ways in which we're imaging them today. So you see in the top, this is from the SOHO, the Solar Orbiting Physical Observatory. And what you see here are sunspots on the surface of the sun, an image of these are images from four different instruments on that observatory. Here are the sunspots. Here's on the surface. This is ultra high energy ultraviolet telescope image, and then you see here an image of coronal mass ejection, which this is actually an image from 2003. And these are some of the sources of cosmic rays that reach us on the Earth. On the lower part, you see an explosion of a supernova imaged 7 years later by the Hubble Space Telescope. And we are subjected to the cosmic ray flux. This shows you a measure of the flux as a function of energy of the particles that are coming to us. And you see here, this is nicely color-coded. There are yellow ones which are solar, and there are blue ones which come from our galaxy, and then there are purple ones which are extragalactic. And although there are many solar rays, they're much lower in energy than the high-energy ones. And these are the high-energy particles that can actually whose products can actually reach the Earth's surface. So those are the ones that we're concerned with measuring. And they're also the ones that are influenced by the magnetic field. So when those that can come past the magnetic field come into the atmosphere, and then we have a cascade of cosmic rays, and everybody here probably knows this. There are many protons and alpha particles and a few heavier nuclei. And then this secondary cascade produces neutrons and charged mesons. And one of the things that it produces, of course, is the example of taking interactions with nitrogen in the atmosphere to produce radiocarbon and other cosmogenic nuclides that are of interest as geophysical and geochemical traces. So there are solar effects on the cosmic rays, and this shows how the daily sunspot number, so the number of those spots that you saw in the first image, varies over time. This is a record from 1983 to 2013. And you see here how this is the solar cycle we're looking at here in the fluctuation of the number of sunspots. That impacts the number of cosmic rays that reach us because the magnetic fields associated with the sunspot cycle basically prevent, when they are large, they prevent those cosmic rays from reaching the surface of the Earth. So you see these two rows in here, the cosmic rays and neutron pressure count on Moscow, basically is anti-correlated with the presence of sunspots and the solar cycle. This lower tracks here are basically X-rays and magnetometer records from the GOES geostationary satellite, which is measuring those things directly in geostationary orbit. And you see a similar tracking here. Here are the number of X-rays as a function of sunspot cycle. You see also the measurements of the magnetic field are impacted in similar ways. So our magnetic field from the Earth is also acting. This is an external variation in magnetic fields that comes from the sun. That's part of the external magnetic field. The internal magnetic field is also acting as a shield for us. In very simple terms, if you have a particle and it's in a magnetic field and its motion is perpendicular to that magnetic field, it will be brought into a spiral around that magnetic field in its motion. Here's the Earth. It has a magnetic field. These are cosmic rays that are coming in. And if they have low energy, they'll be deflected by the magnetic field and sometimes reflected back into space. If they have an energy that's greater than a critical amount, then they'll come into Earth and we'll see the effects of that cascade that I showed you in the atmosphere. And the larger the energy, the more energetic they'll be when they come down to Earth. Of course, the magnetic field of the Earth is not so simple in all cases, and there are complicated factors depending on the angle of incidence of these and place where these particles come in. If they come in parallel to the field near the poles, it's much easier for them to reach the Earth. If they come in at the equator, they're much more likely to be deflected. And here you see some sample trajectories of the kind of paths that these rays might follow. And what you see in here is that this is really a complicated issue. It depends on the energy of the particles, and it depends on the structure of the magnetic field. And over here, I'm just showing you a picture of what the strength of the magnetic field looks like at the Earth's surface and how its structure varies geographically. And you'll see in here that there's this low piece area region where the magnetic field is rather low. And this is actually a place where we're more susceptible to damage from cosmic rays than elsewhere in the equatorial region. So one can take these trajectories and look at what kind of, what spectrum of particles will reach us, and that basically allows you to make a map of the cutoff energy or the energy that's required by a cosmic ray to allow its entry into the magnetic field. And you see in here that the red pieces in here are near the poles. That's where the particles are coming in almost parallel to the field. They don't need as much energy to reach the surface of the Earth. And in the equatorial regions, they need considerably more energy. So you see in the poles, less than 125 megaelectron volts will allow particles to come in, whereas in southern Asia, here in this very green part, you need very high energy cosmic rays to reach the surface of the Earth. So I showed you here this variation with the external field and how that impacts what's coming in. When we turn to longer-term things of interest, which are the things of geological, geochemical, part of the interest in using these particles as tracers, we can't measure them directly, but we can look at the carbon-14 record. This comes from this is an old record now, from the tree rings, 1998 from Struve in 1998. And this can be converted to a normalized production rate from these observations. Then theoretical relations among the production rate, which I'm calling Q here, and M, the magnetic dipole moment, and the solar modulation constant can be used to derive relative variations in the solar flux. So here's the relative production rate from a paper by Muschler et al. And this shows you a kind of surface on which of these relative variations. Here's the radiocarbon, actually in this case this is beryllium-10 production rate. This is the magnetic dipole moment, and this is the solar flux. And these are complicated relationships which we're still trying to sort out, in part because we don't know enough about the magnetic field. And that's actually how I discovered I was working for Lal. Because when I came on the faculty here, he came to me and he said, "You must know things that I want to know." And then we had one of those conversations where he said, "Why can't you reconstruct the magnetic field in the past?" And so, of course, we like to think that we can. And we do that using records from lava flows, from sediments. Here's a sediment core, and from archaeological artifacts which have been fired, and they preserve a record of the magnetic field as it's been as they've been cooled. And we use those to reconstruct what the magnetic field looked like in the past. And so I'm just going to show you my movie of 10,000 years of magnetic field variations. This is from 8000 BC to 1990 AD, and this is the magnetic field strength. You'll see it's much stronger at the poles than it is at the equator. And the blue level here is around 20 microteslas. It goes up to about 80 microteslas at its strongest piece in here. And this is from 10,000 years ago. And I'll just let this movie. Whoop. No, that didn't work, did it? Perhaps it's not going to collaborate for me. Yeah, okay, good. I was afraid we were going to have another PowerPoint moment. So you see how this evolves with time, and you'll also see as we move eventually towards the present day how that low patch in the South Atlantic that I was talking about grows in place. And that's actually a very interesting feature. But you see things that are not unlike it that occurred earlier on in this sequence. And I had the experience, actually many times over the years as this work has evolved, of showing these kinds of movies to Lals, and he said, "Oh, I don't believe in modeling." And I said, "Well, you don't have to believe in modeling, but you know, these models are based on data. We can look at the data if you like." And so we looked at the data, and he said, "Oh, are you sure that's right?" And as you know, one has many conversations of these kinds, and he's always very challenging, and he always makes you go back and do it again and make sure that you are right. And that's always was always a wonderful experience, actually, after one had convinced oneself that one was right. So this shows actually a longer-term view in here. This is something that we've also worked on here. We specialized in trying to make global views of the paleomagnetic field over timescales, on millennial timescales, and then on million-year timescales. And this shows you that feature. This is the dipole moment estimated for the past 2 million years from globally distributed records. So the piece I showed you before was just this very top piece here, very little piece here. This goes all the way back to 2 million years ago. You can see these marker points that are shown here. They're typically excursions of the magnetic field. They're places where there are lows in the field strength. And those are also associated, as is well known to most of you in this room, with highs in the cosmogenic isotope production. So this is, of course, these things that I did for Lal, even though I didn't know I was doing them for Lal, tremendously interesting to my perspective. But I come back to the fact that when you look here, this is a measure of the power spectrum of the magnetic field as a function of frequency, and frequency here is in per million years. And one of the things that we are still not able to do adequately is to separate the production rates, the geomagnetic changes, and the solar climatic flux changes. And this spectrum, it's a work in progress. The place that we are not able to tell people enough yet is in how rapidly the dipole moment can vary on these relatively short timescales. So the past 10,000 years is in this frequency range here. So this is 1,000 years, this is a 100-year period. And that's the legacy that we have here. We're still working on the things that Lal was doing way back early in his career when he wrote those great review papers. And even his last papers, he was still saying, well, you can't tell me what I need to know about the magnetic field, so I'm just going to assume something.
So for those who don't know me, my name's Jeff Gee, and I've been a friend of Lal's for a long time, and actually when I first arrived at grad school, he tried to convince me to become a student of his, but I wasn't successful. So anyway, I'll be moderating this next session, and I think we'll go ahead and get started. So the first talk is going to be by Goswami to say a little bit about Lal and planetary science at PRL.
Good morning, and it's a honor to be here and talk about my mentor. So I thought it is good to show his mentor, so Bernard Peters. And then, but there is one more mentor of him just for a year, and that I will come to you. And then that is the group of geophysics group at TIFR. I landed that year. I'm somewhere there. But what I'm showing you, you see some participant from Scripps also. Sheila, you can see yourself somewhere next to Mrs. Lal or something on the top right corner. You are there. So that is the SIO connection. So I come there, I find these people coming from Scripps Institute of Oceanography. I said, what they are doing at TIFR? Of course, we have the ocean next door. That was nice. Okay, then I think you can see Lal little bit relaxed when he was in a conference. And then right to him is what we call Professor Rama, who is also there in the second row in this middle picture. For at least 3 months, when I was not yet a student, direct student of Lal, but I was going to his lab for some project work. And then I thought Professor Rama, who looked very dignified, is the head of the group. And I know that Lal is head of the group, but I was thinking it is Professor Rama because Lal comes with some flags, this, that, and then, looks like a very heavy-wheel guy and storming all over the place. And then, so I thought that cannot be a, head of the department and a professor. So, and then, of course, my entry to this group was very different. I'm basically a nuclear physics person. We have been told many things in our university days, although it is in a place called Guwahati. There are people who have done PhD in UK and US, and then they told about this resonance particles. So I want nuclear physics, particle physics. I go there, I said, that, what do you want? I said, I want to work on this, new detectors in Europe. They have some data here or something like that. Then the gentleman, he was very nice. He said, they have only pictures. You will only measure pictures. You will not get anything real. I said, what do you suggest? He said, there are people here, they are doing lunar sample. I said, I don't want to touch rocks. Okay, no, they are doing cosmic rays. That is, I know, because we were taught cosmic rays. I say, I'll give it a try. And that is where I had this confusion about who is Lal, who is Tamane, who is Venkat, who is Rama, and who is who. But then there is something called, my colleagues used to tell me, my student friends, after some time, when they said, lunar sample, so I said, okay, maybe I will give it a try. But I was never called to what is called Bull's room. I don't know what they are discussing, So there's a room. So I thought that until I get an entry to there, let me see what I was just polishing some meteorite samples. I'm not interested. Then one day, suddenly, Lal, now I know who is Lal. He comes and then just asked me, can you do this? I don't know what. I said, he likes equations, differential, integral, everything. So I could do it. So next day he said, why don't you come in? So I was inside to that Bull's room for discussion. And then for about a year, I don't know what I was doing because I was never told what I'm doing. I'm just doing, that's all. And then I think he liked, and I think I missed all my dinners for about 3 months because he comes at 5 p.m. to the lab and goes at 10 o'clock. I come from a background, professor is very great. I mean, how you can go out for dinner when he's not taking dinner? But one thing is good, which sometime I realized that if I miss dinner, it is not bad. I will get a beautiful dinner made by Devendra Lal at the home. And the home session starts around 8 o'clock and goes up to 11:30, 12. And if I don't have anything, he will arrange that I will be dropped also. But sometime, you have to get his confidence, to sometime argue with him. And once he feels you are okay, then he gives the freedom you cannot believe. And in Lal's home, I remember that whenever Mrs. Lal or Devendra Lal feels that I am crossing the border perhaps and there may be a catastrophe, there will be a sound, Goswami, do you need coffee? I knew what it means. So it is not a normal student-teacher's relation. It is something different. I cannot explain what it is. I could not replicate it because I was not very sure if it is good or bad. So I'm very nice. I'm not very nice to my students, but I never had that coffee or dinner at home so often that I had. And those were better dinners than what TFR people will cook. So what I want to do, I want to take you for a few minutes through something which I thought how his career evolved. His first person he worked with called Taylor. And he's a British person who came to TIFR to start cosmic rays. And then he landed up as the vice chancellor of the university I come from in Assam because he was a missionary. He went to Shillong and then he was teaching there. Then he became the vice chancellor. His first paper, I wish we can write papers like this, just how many, 20 lines in Nature. So an unusual pi mu decay. So he started with real hard cosmic rays, but then very soon, so he came down to Earth. I mean, this is the first paper, cosmic ray produced beryllium isotopes in rainwater. So you see Rama is there, P.S. Goel, Jha, Lal, okay, so all of them. So this is the first paper. So he already moved from cosmic rays to its interaction on Earth. You go that time, this was in Scripps. I mean, I have to read this paper to make a counter with Professor Bhandari as a graduate student because these are project works. So this is something I think the other gentlemen even opened probably some business with making this counter very nicely. But this is something, I just remember this, I think first Scripps, something which impressed me. Then, of course, now this is Silicon-32. It was Professor Soma and him. It was like a lifelong affair. And you see, this is something, again, it's in science. I mean, these are something I thought it's a kind of landmark, although it doesn't. He tried little bit of me to give some of this stuff, but I said that I don't want to get into something which I feel is not my cup of tea. I have to learn too much from you. So then you see, then it comes what I like. Okay, meteorites. Okay, I touch moon sample. I love meteorites. At least they look not bad, and they may have something to tell. And you see, this is again, cosmic ray intensity in meteorites. They already talked about what pulse should be look like and what. And this is, everybody talks about this. I mean, I read it, and I have met many people now, person who visits PRL as the director there. Sometimes I say hello to them. And there are a couple of gentlemen, only about 3 months back, he said, "Oh, Lal, we had to read that paper when we were graduate students." I mean, and he is already plus 60, actually, the person who is there. So I think, it tells something that even today, quite a few people talked about this paper. So this is still at Lal is at TIF. Okay, now Lal moves to PRL, but not yet. So this is Sundar is here. So this is one of the first observation of single grain irradiated in space. It is inside a meteorite from solar particles. Also, the picture doesn't look very good. If it doesn't convince you, later Lal likes to do chemistry. He is subject to physics, but as a student, he always used to make ink, paste, and he is a chemist not by training, but he used to like to do it and photography. That was his second thing. The picture in 1971, he's not there. I thought maybe he was the photographer. I forgot. So, but you see, nowadays, if you look tracks, you know how to etch it nicely. It would have looked like this, if you would have waited 5 years. But this is the first time there was another group in France. Both of them did it together. So that same type of work. And then you see, now this is another one. This is olivine. So, see, this is the most common mineral in many of the meteorites, and we don't know how to etch it properly because it will go directional. You cannot do anything about it. These all things, this has happened when I was there as a first-year student. But there is, I used to cut I told Krishna Swami, he's here. Certain thing, I don't know how Lal found this mixture. And today, even before I was asking, I said, I don't know, because it has a lot of acronym, and they finally think this HN is called WN. If he has started with A and with all the permutation combination, I don't know when they reach WN. But I try to tease Krishna Swami because the authors, you see, Krishna Swami, D. Lal, then next is Nanda Prabhu, who is now Mrs. Krishna Swami, and A.S. Tamane. So I said that you must have, Swami, he was the pioneer in this. I said that you must have thought it should be, your wife's name should be H in the ancient. So with Nanda, W-N. So I don't know if it is correct. Krishna Swami will never agree that it is correct. But anyway, it's something. Okay, so you see what happened because of all this development. A new tool to study past records of solar and galactic cosmic rays using lunar and meteorite sample. And Lal got a sense of nuclear track at the very early stage and could convince Buford to visit TIFR. I think they learned all the tricks from you, or whatever it is, initial one, and then Lal can, of course, once he knows, he can expand like anything. So, and anyway, so you see, Hardlock Cosmic Ray Archaeology. I don't know. We have an archaeology lab in TIFR started by him to do carbon-14 dating and all this, civilization, Harappa and others. And then he used the word cosmic ray archaeology. I don't know if I like it, but it has some interesting. So this is also a very important paper. This came on Space Science Review. Then he has a very strong way of making student work. First, he will give you some work, experimental work, which is already hard. Then he will give you a lot of equations. Now you solve it and do something. So he made me and Bhattacharya, about which somebody talked. So we two had kind of in a guinea pig. He has all sorts of different geometry, this and that, how the tracks will produce or what will do. And finally, of course, we wrote a very thick paper in rocks exposed on the moon or in free space and isotopes and tracks. So this is in the first 2 years. And then, of course, we did some experiment, and then in this particular paper, I don't think I had great contribution, except that I just showed that if there is something like erosion is going on, whatever you see is not the correct, you have to make a correction. And somehow it was an easy equation to write, so I have my names there. So, but one thing we liked, at that paper, we said that if you see ancient heavy nuclei, it looks like that heavy iron nuclei are enriched over iron nuclei compared to what we know at solar when it comes out. And the very next year, I think his PhD thesis was that, and then there was a balloon flight, I think, and then there also they found the same thing. So we are happy that nature is remaining the same, sun is emitting similarly 4 billion years ago and now also. And so I felt happy because I was not very comfortable because I have not done anything except doing those calculations. Okay, so now, you see, you do not know, Lal is there from space to ocean, so he is everywhere. So since I am mostly on space sciences, so this is again thanks to Buford, there was an exposure in Skylab. We got some plastics. Now we know how to etch plastic. We did something. So there's some work but what I'm telling is that anything he gets somewhere, I mean, he has so many friends. I don't know how his friends in USA failed him whenever he goes for something, and he generally gets it. Whether it is a sample, discussion, you'll make sure that, and that's a very different way. I can't do it. I mean, I feel after some time maybe that person is not feeling okay, but I think he has a very good art of doing it. I mean, that was great. And then, you see, we have a space shuttle experiment after this. This was an Indian experiment which went on space shuttle in Space Lab 3. And then he was a part of it when we wrote it, the proposal. But he was coming more often. He has gone out of, TIFR at the PRL also. This was in 86. He left PRL in 83. And then he came even to Houston when we were flying this instrument and had some problem. It worked out fine. But he very politely and firmly told, no, my name should not appear in any of these papers because I have not significantly contributed to it. I wish I could have told when I was a young student that, no, I have just done an equation. Don't put my name. But that time I thought, okay, I didn't realize that. I should have probably asked not to put my name. But anyway, so this is, and we had a very good, this is what talks about, then, see, we have now from optical microscope to SCM and TEM, because when he moved to PRL, the first thing he got, we used to tease him, see, when in India in old time, when you get married, then the girl's side has to give something, for sure, your liking. So I think Lal made a deal when he moved to PRL that we must have at least a scanning electron microscope. And then, I mean, it was very useful. Because what happened, and it is very important also, because once we had the scanning electron microscope, it was allowed to be used by any university people all over India free. And so me and another gentleman called V.G. Shah, who was a technical person, we have to help them. And I liked it because when I came here, I learned in 1979, I came to do some work with McDougall, but then there was a new electron probe came and Ron, what was his name? That our EPMA person, McDougall? So he was my teacher basically, and so we used to spend a lot of time. So I learned a lot about the electron probe, and so it was easy to set up the SCM in India. So this is something, again, character of Lal. See, in India, all meteorites that fall in India is a property of Geological Survey of India. We cannot touch it. He broke the rule so much that now GSI doesn't talk to us because we just go and get it. So this is a meteorite that fell in Gujarat. Big meteorite that fell, and people have seen it coming. And he disturbed everybody from, Menon, who was a very well-known person in the government at that time. So he got military, he got helicopter. Then he went to the villages. So that's why I'm saying taking science to the villages and schools. And then you see this is all school children, and it's a bad place to look for meteorites. All rocks are black, okay? And then you cannot imagine, we collected so many kilograms of it. And then you see, he's very nice. He's in the field. He's taking a little piece of meteorite somebody found and gave it to him. And then all this, strewn field. You see all those pieces. These are all collected. And it is a very important, and he spent a lot of time. See, I don't know how he finds time to do all these things. But he and of course, one of the greatest things I must tell, there is a saying that after every successful man, there is a lady. And I think without Aruna Lal, I don't think Professor Lal could have done what he has done. I mean, it is extremely important. Even he was controlling all of us, she was controlling all of us, like, in those home and taking care and all this stuff. So again, you see, it continues. This Bob Reedy already showed you. You see, he's talking about solar system matter, which I'm interested. That's why I'm picking up these things. Then you see, this is inside to produce. He loved accelerator mass spectrometer. It must come sometime or other. Tim Joule got the brunt of it whenever he wants to do something. And I can only tell that then we have to review papers. I said, no, I don't have the time or patience. He said, no, you must write. So that was, I was just plus 30, and then he made me write this paper, and Laurel Wilkening, who was here, and then I visited her in Tucson, and then it was a very interesting experience at a young age to how to write a something like 60-page paper, or 70-page, and it's not very easy. So I don't write them too often. Okay, then this also Bob Reedy told, you see, we wanted to do something with solar flare particles, so there was no great compilation. There was a cosmic ray meeting in 1983 in India. So Bob Maguire and few people were there, so we talked about it. So this took about 4 or 5 years to make this, and I think after that nobody's really taking up to do the other cycles. It's a kind of routine and laborious, but when the fruit comes out, it's quite good. Okay, planetary materials, a new beginning. I think this is probably next 10 minutes. Sorry. So you see, the lunar sample made a tremendous improvement in various laboratory techniques and including mass spectrometry. What Lal did, Lal invited 2 young persons, Professor Gopalan, not so young now, and M.N. Rao, to India, to TIFR, to start mass spectrometry. Okay, and what we have now, and of course very soon they all moved to PRL. So in PRL we have noble gas, rubidium, strontium, argon mass spectrometry laboratory because of them from 1980s. And then with this strong background, nuclear track, already Professor Bhandari was also involved. So, and he does radioactivity. So it was a very strong group when we were doing the lunar sample in that time. And then it still continued. And I told about this scanning electron microscope. It was given free to everybody who wants to come. And Lal coined this work, geocosmophysics. Of course, after some time, that was the name of the group we are known at that time. And now you will see the number of micro. See, this is one thing, SIMS, the secondary on mass spectrometry, it took me 7 years to get it. Because, and I must tell you, without Lal, probably it would not happen. When we have a 5-year kind of plan, so you have to write early. At 81, so I was thinking we need an electron probe. SEM is not enough. I remember Gopalan told me, write something better. Only thing I know better is something which I have not seen, but which excited me. It is an ion probe. I think you had it, and another gentleman had it, and I read about this 77 paper by that time. It looked interesting. So I still remember, you will not remember, I wrote him a letter that we are going to get an ion probe. You have already made the perimeter. Maybe we'll paint the wall a little here and there. And then I think we could do it a little. And you see, we have all this mass spectrometer now. NanoSIMS has come, MCIC PMS, laser probe, NGMS, TIMS, and we are about to order an accelerator mass spectrometer. It takes time, but it will come. So all this because he started something. My last part about planetary exploration, because India has gone to the moon. I was not very keen about it, but anyway, so we have all these samples of early solar systems. You have these unprocessed meteorites from which you can remove refractory objects, spherules, which are some of the first formed solid in the solar system. Then you have these processed meteorites. They are either stony iron, or melt and solidified. You can analyze all this sample and make a story about the early solar system. This is what I have spent most of my time. What we feel we can make some story like this. Okay, so these different samples give you time scale at different stage. I put 2 in red. That is less than 1 million year. We have found something called calcium-41, which make that constraint that first solid must have formed within 1 million year. Then we have also found long looked for Professor Urey's aluminum-26 at the heat source in a meteorite that fell in India called Piplia Kallan, and it was a science paper in long back, 1999. So that made that some of those chondrites has to form within 3 million years. We had a big problem because another gentleman using much superior hafnium tungsten said we may be wrong, but after 3-4 years, we have to wait until 2002 when 2 groups found that, and he also agreed. Nice gentleman, he's in Cambridge now, very good friend, who has initially made a small error that his starting zero was offset by only 2 epsilon, and that makes a lot of difference. So for a while, people are not very sure if we have done it correct or not, but we got this. So these 2 results at least come from PRL in planetary sciences. So now, so you see, again, story keeps on changing. See, in 2005, things were going up to 10 million years we need. Now we do not know. It looks like everything has happened within first 3 million years, whether it is iron meteorite or any other meteorite, and still it is continuing. Okay, these are some of the people who did this work in PRL with me. And then, see, this is just, I will take 2 minutes, okay? I'll close it without reading much. In 97, when India said we should go have a lunar mission, I was not very excited because I am not sure whether ISRO, that Indian Space Research Organization, will be able to make it, whether we will have enough funds to do it. So, but Professor Vandari, who was about to, see, in India, 60, you are very old, you have to retire. So about to retire, so he took the lead to make the initial plan, what science we should do. And finally, you know, in 2003, when the government approved it, so somebody came and told me that Department of Space has given you enough. Now you have to give back your time to department. So I became the in charge of the moon mission. So from 2004 onwards, I had a difficult time, but I am happy that it worked well. So these are the missions that we have performed. The Chandrayaan 1 has already gone. 2 years supposed to go with Russia with a lander, but because of they have some problem with the Mars mission, it may go altered. Mars, we are planning to go this November because of this. And so I think we have a good planetary exploration program now. We can afford it. And so Chandrayaan 1 mission, of course, you have heard here that they claim we have found water. No, it is hydroxyl and water molecules stuck to the surface of grain. And then, of course, we thought that there is water below the surface also. The L-Cross mission has impacted one of those sites selected by us. And then they found something there. So I think we are close to that. And there are many other interesting results. But I think this is the right-hand side graph is the result for water. And we have the polar region, we have more of it. And I must tell you, see, when the Chandrayaan 1 mission goes up, only change I have made, it says it should not be a technology mission, it should be a very strong science mission. And I found that we had difficulty with our own instrument because we cannot get the high-end instrument because of dual purpose. So the chairman, although he was a technical person, I said that if you want science, we cannot do it alone. Let's go global. But in a different way. We ask only individual to propose, not the mission, not that like a NASA to forward through it. So we got very beautiful instrument, and that's why we could compete, and we have some new discoveries also we could make. Of course, now we can get most of the instrument. In Chandrayaan 2 and Mars, we will go alone. Okay, so actually, whenever Lal comes to India during winter, he comes for 1 month or more. He talks excitedly about all these things. He will discuss with me for hours what I should do, but he is some now it is, you people you have to do it. He will only advise. But it was very interesting. Like all of you know, if you talk with Lal, he will always find 10 faults with you. And then you come back, am I that stupid? Maybe I am. And sometimes, yes, I know that I was stupid. Okay, so, and Mars mission, anyway, there are some standard science questions that will, but let me show you, this is almost ready to go. All the experiments are there, and these are the main 5 instruments, HD ratio, methane, then thermal infrared spectrometer, and then atmospheric studies. So these are the things we will do, which are very important, and we are thinking we'll go. This will also come up sometime. It will have a lander and rover. We are making all the instruments, but except for the lander they are making, we have some discussion. And they had a problem with the Mars mission, so we are not sure about the time scale. So last, I just want to tell that we have recently developed in Institute the 4th instrument, because you have to do it to look for exoplanet. those who are moving outside, because in US there is two methods. One needs huge telescope, but in Swiss and France and some other people, they are making with small telescope that can work, and we have that. So we had a meeting in last January. Lal, I invited him that he was supposed to come. He was very excited, but it didn't happen. He couldn't see that we can, but he knew that we can detect now exoplanets. I remember Phil Morrison coming and giving a lecture some 20 years back that, see, we feel how stupid we are. We have only one planet. And it is like, for a biologist to just looking at one, particular species, tell how whole world is. And he's right. So we don't know if we are an anomaly or we are for real, our solar system. I think I will stop here, and thank you for your attention.
I do not have many pictures of Lal, only one or two of them. I thought I'll show this picture because it's the only picture where he gives some impression of listening to me. So let me go back to how I came in contact with Lal. I submitted my PhD thesis in the early 1965. The thesis must have gone to a geochemist, but it was sent by mistake to a physicist who happens to be a colleague of Dr. Lal, the Tata Institute of Fundamental Research. Dr. Tozer, who received this thesis, could have written the thesis saying it is not my specialty. But luckily for me, he referred my thesis to Dr. Lal for his opinion on the experimental work I had done. Lal must have, I don't know what he said, Lal must have said something positive about my thesis, and my thesis, I was given the PhD degree. In those days, we had to wait at least for 1 year for this evaluation of the PhD thesis. So we used to write for postdoctoral proposals. So I wrote to Dr. Wetherell at UCLA for a postdoctoral position. Dr. Wetherell had received a handwritten letter, and I had not published any paper at that point of time, so you would be wondering what I have done by way of research. Luckily for me, Dr. Lal, who had seen my thesis in TIFR, had moved to UCLA just in the 2 months' time, and Wetherell thought of asking him what he knows about Gopalan. So once again, Lal said something positive about my thesis, and Wetherell, when he gave me the postdoc position, he told me about Lal's views about my work. I was not in contact with him for a couple of years because he moved to Scripps here. In 1969, since I was a Fulbright scholar, I was asked to go back to India after 3 years. You can't stay beyond December 1969. So I went and met Lal here in the Scripps office for what kind of job prospects I can have in India. He said I can join his group in Tata Institute of Fundamental Research, which I gladly joined in April 1970. Few days later, he took me to a corner of his laboratory and showed me bits and pieces of a mass spectrometer, and told me I can put them together. I had seen the same kind of mass spectrometric parts in Wetherell's laboratory, so I was a bit confident I can put them together and make it work for medium strontium dating. So I started working for a couple of months, and then he called me to his room, which I got a very beautiful view of the Arabian Sea as you have got here, and then waited for a few minutes and told me a very intriguing statement. Gopalan, when we eventually meet the God, he will ask us what we have done for others, not for ourselves. I do not know what to express to tell him. He came very quickly to the point. He said, Gopalan, you please stop working on the metal mass spectrometer. Try to build a Reynolds type glass mass spectrometer. Because there was another fresh recruit, Dr. M. N. Rao was referred to. He had come back from America after having done noble gas studies. So if I can make a Reynolds type mass spectrometer for noble gases, both of us can study and use their machine. I had not even seen a glass mass spectrometer, even on making that one. But I was only on a temporary appointment, so I had to take seriously what he wanted me to do. Maybe because of beginner's luck, the machine worked very well, and Dr. Lal was very pleased with what we could achieve, and I got my permanent position also because of that achievement. while we started to work on the machine, myself and M.N. Rao, maybe a year or so, then we began to hear news that Lal has accepted the directorship of the Physical Research Laboratory in Ahmedabad, about 300 miles north of Bombay. And also this entire group will be moved from Bombay to Ahmedabad. Lal must have anticipated that some of us at least will have some reservations about going from Bombay to Ahmedabad. And I suspect, at the time, Professor Arnold and his wife were visiting India. I think Lal must have told them to give us a pep talk to move from Bombay to Ahmedabad. So we moved to Ahmedabad, and the laboratory was not ready for the kind of work we were doing. We took almost 2 years to again start the kind of work we were doing in Bombay, but we learned quite a bit about how to get going in laboratory facilities. That is the time I also switched over from rare gases and moved to doing rubidium strontium dating, trying to rebuild the old mass spectrometer. This is the time Dr. McDougall wrote from here about a joint project between Scripps and PRL on the study of the Deccan basalts. Lal was very excited about this project and gave full support for this program. And because of that one, this collaboration between PRL and Scripps has been very productive and has been also operational for a long time, and only ended when Doug decided to leave in 2005. I must also tell here something about Lal's way of doing creative work. When he became the director, he set apart some amount of the research money, till anybody in PRL can come up with a good idea or an interesting idea, he will give that money for him to try out that experiment. He must have been disappointed because even after so many years, there were not many claimants for that kind of money. In 1983, he decided to step down as a director, as was mentioned here. And I also moved in 1985 to another lab in southern India. And all this time, Lal has been in touch with what I was doing, including my role in the establishment of AMS, the first AMS in India, with tremendous help from Dr. Jal and Dr. David Elmore. And I was surprised when Lal, when he saw that instrument in the laboratory, he nominated me for the AGU award for what they say, the unselfish cooperation in research. I did not get that award, but I cherish that sentiment, what he felt, that I had done something during this 25 years, and I will always cherish that sentiment of him all my life. Thank you.
This won't be a science-based talk, and if he were here, Lal would quite possibly be disappointed about that, because he found it hard to conceive of life without doing science. I can actually hear his voice in my head in the way that only he could say it. He'd say, "Sir Doug, let's work for the next 5 years, night and day, and then you can do anything you want." The thing is, he would say this repeatedly, once or twice a year, over the 40 years or so I knew him. So I came to think of it as Lal's sort of rolling 5-year plan, always extending further and further out into the future. I first encountered Lal in 1969. I was a first-year graduate student here at Scripps, and I think encounter is the right word to use with Lal, by the way. And there was a course listed in the class schedule for the spring quarter called Nuclear Geophysics. At that time, Lal was spending most of his time at TIFR, and none of us graduate students really knew him. So I asked Ed Goldberg, who I think must have been the student advisor at that time, about the course. And I don't remember exactly what he said, but basically he said, "Lal's a brilliant scientist, you should go for it." And so I did, and that was the beginning of a long association with Lal. His course, that course in nuclear geophysics, was probably the most difficult and at the same time the most exciting one I had ever taken. he'd come to the class, and at the end of the class, he'd give us a problem set. And he'd say, oh, this will only take you guys half an hour or so. Well, of course, we'd be working on it for about the next 3 days, because basically a lot of the problems he assigned us were straight out of Lal and Peters. We were calculating cosmic ray production rates at different latitudes and all these kinds of things. So it took us a lot longer than half an hour, that's for sure. And sometimes I think we all wondered whether we really should be in that class. But we learned a lot of profound things in that class, in addition to the nuclear geophysics. We learned what it was like to confront real scientific problems, actually, because Lal's problems were anything but cut and dried textbook problems that we had been used to. We learned the value of back-of-the-envelope calculations. Back of the envelope was one of Lal's favorite phrases, as was quick and dirty when he was talking about experiments. We learned how to use slide rules effectively. This was before the days of hand calculators, and somewhere in a box somewhere at home, I think I still have one of those yellow plastic slide rules that Lal used to give out to people in his classes. We also learned what a generous man Lal was with students. And this was something I saw over and over again in my long association with him here at Scripps. He really loved to work with young people, and he loved to encourage them and to impart knowledge to them. In that 1969 course that I took, he was rarely too busy to sit with us, often for hours at a time, actually, if we had difficulties with his problems. And this is a picture of Lal, a young Lal, sitting with an even younger student, doing what he really liked to do, and that is talk to students. Many years later, Lal and I actually co-taught courses here at Scripps, and I saw the same thing. He'd often complain about the preparation of the students in math and physics, but when the time came, again, he was extremely patient. He'd sit with them, work with them for hours. He really cared deeply about education, and he put a huge effort into any of the classes that he taught. For many years, he voluntarily taught undergraduate seminars on the upper campus, and these are meant to introduce first-year students to interesting topics and interesting faculty members. And with Lal, they certainly got both. Charlie has already mentioned that he set up a scholarship fund here at Scripps for talented students. And as you might expect for anybody who was a fan from Lal, because he was a fan of lateral thinking, he also had a few sort of off-the-wall ideas about education. And there's one I remember particularly well because it involved our son. When our son was 4 or 5 years old, Lal decided that actually the way to introduce him to formal education would be to teach him quantum mechanics. So I don't think he thought through the reality of trying to do that, and it didn't happen, of course, but it's the kind of thing that you sort of came to expect from Lal. Not long after taking his course in 1969, I found myself working in his lab. Gustav Arrhenius and Lal were co-advisors on my thesis work. The whole field of particle tracks in solids was relatively new at that time. Lunar samples were about to arrive at UCSD, and it was just an incredibly exciting time to be working with Lal. He was always in the lab. He was there all the time. He was an exacting taskmaster, I must say, and sometimes it was a little exasperating to work with him. I think, as you've probably gleaned from some of the things other people have said, he would come up with all sorts of ideas, and he'd push them, and he'd push them, and he'd push them, and you'd think, you know, throw up your hands, this isn't going to work, but actually many times they actually did work. Many times they didn't also. He always carried around 3x5 index cards in his pocket with lots of pens, and whenever he encountered an interesting idea, he'd write it down. And it didn't have to be directly related to his science, as many of you probably know. I remember for several years he experimented in the lab with ways of suspending titanium dioxide in various kinds of fluids because he wanted to invent his own variety of whiteout. I think probably a few of you in this room probably remember typewriters and whiteout. He was tremendously inventive. One example from the early days of track work that really impressed me was the method he and his students at TIFR, including Sundar Rajan, who's here today, to study the chemical composition of heavy nuclei in cosmic rays in the past. And the idea, which wasn't a new one, Buford and others had worked on this problem, was to measure the lengths of tracks in minerals from meteorites. But Lal's approach to this problem was really ingenious. This is an illustration from the paper in 1969 in Nature which described this approach. And the meteorite minerals had to be polished flat and etched chemically to develop these tracks. And of course that meant you could only measure the lengths of tracks that intersected the surface, so you were only measuring partial track lengths. Lal's idea was to etch the hell out of these grains so that tracks that intersected them, these ones that are crossing and were completely confined within the grains, would become visible, and then you could measure the total track lengths. Lal called these things tints, standing for track in tracks. He also coined this term tinkles for tracks in cleavages or cracks in the mineral grains. But Lal being Lal, he actually wanted to call these things tits. Now, I don't know whether it was a journal editor or whether it was Aruna who eventually quashed this idea, but surprisingly, when I looked up this paper in Nature just recently in preparation for this symposium, all through the text, of course, they're called tints, but Lal somehow slipped in there in the figure caption, and nobody apparently caught it. Aruna, of course, as I think a couple of people have already said, was really the love of his life, and he thought about her constantly. And in 2007, I opened my email one day and found this picture which someone from PRL had sent him. And this is from a cosmic ray conference in 1963 in Jaipur. And there are a number of luminaries in this picture, but at least including the Prime Minister. But at least for me, Aruna is the one who's really the luminous one in this picture. She was a constant presence when they were at Scripps, and she was a tremendous influence on those of us who got to know her well. Lal depended on her for everything, as you've already heard, for library research, for university paperwork, to keep things organized in his lab, and he relied on her for coffee. Goswami, I have a variation on Goswami's coffee story, actually. Lal liked his coffee made with hot milk and with instant coffee stirred into it. And not my favorite kind of coffee, I must admit, but anyway, I ended up drinking quite a bit of it. I was lucky enough in 1971 and 72 to spend 6 months at TIFR when I was finishing up my thesis. The idea being that I'd have the benefit of Lal's advice while doing the writing up. And like Goswami, I remember many evenings sitting in his apartment in the TIFR housing complex talking about my thesis work and talking about science in general. And every once in a while, Lal would sit up and he'd say, "Aruna, Doug wants coffee." Of course, I hadn't said anything about coffee, but very soon, 2 cups of milky Nescafe instant coffee would appear on the table. There's a lot more I can say, but 10 minutes, of course, can't do justice to a long association with Lal. And all of us, as you've already heard, and as you'll hear more as the day goes on, have our own memories and stories to tell about Lal. And they're all unique, I'm sure, but I think what's common for all of us is that his departure from this world leaves a big hole in our lives. Thank you.
This is a rare picture of Aruna and Lal, In the Antelope Valley, north of Los Angeles, we managed to convince Lal he didn't have to work one Sunday, and with Aruna's help, of course. My wife tells me that Aruna actually had checked out the Antelope Valley in an earlier year to see if it was up to Lal's standards for not having to work on a Sunday. And anyhow, Lal was at UCLA in 66, 67, and 83, 84, and I'll tell you a bit about that. They visited my wife Gudrun and me on many other occasions, and I won't tell you very much about that. Let's go on to...
Just the arrow here will work, I think, or the space bar.
Oh, space bars. Without glasses, I can see the space bar. I was guessing that Lal had arrived here in 60. I've now learned that that he arrived in 59. Is that right? Yeah, okay. Anyhow, I was in Germany on a postdoctoral fellowship, but I had gone through ROTC and had to serve 2 years in the Air Force as a second lieutenant, which I mean, the Air Force was very kind to me. They let me keep postponing this while I got my PhD and then while I had this NSF fellowship. But eventually I had to go in, and I went in the fall in December of 59. And then Gudrun and I decided to get married, and after 2.5 months, I had earned 2.5 days of leave, I think, and which with signing out of the roster books with the help of my friends, I managed to get to Germany and get married and get back again. Shortly after that, Lal was, who was already a famous guy at that point, had been invited to give a talk at the American Meteorological Association. I was working in a group. In fact, they had put in what they call a square peg request for some random scientist who was educated in nuclear chemistry and who could work in their lab, and I was the only second lieutenant in the Air Force, at least going in at that point, who had a background in nuclear chemistry. We had already made our acquaintance when I was at MIT with Ed Martell. Martell was a student of Bill Libby, and Ed knew a lot about Lal, and later, as I was looking at Lal's bibliography, I realized that there were at least some unpublished reports or some sort of marginally gray literature reports of collaborations with our group at Air Force Cambridge. Anyhow, I got assigned the job as this naive guy who had never been very socially gifted, and Lal, who hadn't been in the country very well, to look after Lal when he was in town for several days. And my most memorable experience is that I picked him up at a hotel early in the morning, and he says, well, I'm a vegetarian, and I really would like to have something delicious. Do you suppose you could get me a pizza for breakfast? And I mean, now I would never try it. I would know pizza restaurants don't open in the morning, but in those days, Lal and I spent an hour or more exploring all the Italian restaurants in Cambridge and across the river in Boston, and never finding a pizza restaurant. I no longer know what Lal finally ended up compromising with for breakfast. Anyhow, I wanted to tell you some of the, one thing that Martell told me about Lal. He said, well, you know, Lal got his education at the Tata Institute, and he was very fortunate to have Bernard Peters there to teach him about this, and I learned about Peters having been a communist and how he
for whatever reason, it's not, I've been listening to what other people would say. It's not clear that he actually had to go to India and leave his job at the University of Rochester, but he was worried about whether he might suffer damage because Oppenheimer had revealed that he had been a member of the Communist Party, but also that Homi Bhabha had convinced him that doing cosmic ray experiments on balloons in the tropics would be a good thing for him. Anyhow, one of the things Martel told me is, they don't have much research money in Bombay, and so, but they're very good at making beta counters. And they make a new beta counter every year. And that was the first several years that I knew Lal. I mean, he was always publishing another paper on a new kind of beta counter. And when I heard this story, it reminded me of the time I was in Bern when Kurt Marty was there, and it seemed that everybody who worked with Heldermans or Johannes Geist had to build a new mass spectrometer. So it's apparently some experimentalists in the world followed that model of educating young people. That didn't get me an advance here. Anyhow, I was very lucky. I mean, not only did I not have to be a regular Air Force member, I had to be officer of the day something like once every 5 months, which involves spending the night there and taking over the UFO reports that might occur during that night. But I had lots of time on my hand, and I was very interested in meteorites. I'd been educated as a nuclear chemist, but I knew nothing about meteorites. But I had decided I'd made a mistake, and I didn't want to spend my life as a nuclear chemist. In fact, I had heard talks by Hans Suess, Jim Arnold, and Harold Urey while I was at MIT, and I thought, well, those guys have educations, have backgrounds similar to mine. I bet I can follow in their tracks and move into meteorite research. Anyhow, but while I was there, I got the idea that radioactivity was not only made in cosmic samples by galactic cosmic rays, but it had to also be made by solar energetic protons. And I think this is the first paper that ever attempted to model making radioactivity by solar flare protons, but because their energies are not too high, you want to, the penetration depth is low, and they're sort of ideal for making radioactivity in interplanetary dust. And I predicted that you should be able to measure 26 aluminum in sea sediments, and later we seem to have been successful at that. Anyhow, as needless to say, Lal and Arnold and some other people were my heroes in this regard. I was trying with my primitive level of understanding and with no senior person giving me advice to do these numerical integrations as best I could. And when this paper came out in '63, I showed it to Lal, and he was upset with me. He said, "Why didn't you tell me you were doing this?" And I thought, you really don't know, Lal? I mean, he was my competitor, and he was so fast, mentally so fast at writing papers. I wanted this paper to be published in '63 and let Lal's improvement on the technique to be published in some later year, not in '63. A question is, why did Lal spend 66, 67 at UCLA? And I'm convinced, and Lal told me this too, that he came there to somehow absorb from the aura of Willard Libby, who was at UCLA. I mean, and of course, Arnold had been a postdoc with Libby when the carbon-14 method of archaeological dating was developed, and I picture that that Lal thought of himself as being in some sort of succession of high achievers in modeling cosmic ray effects in the Earth's atmosphere, and that was one part of it. But it developed that, yes, he did want to work with Libby, and what did he want to do? He was searching for something to do with Libby, and they finally came up with the idea of doing a space experiment. And I had told Libby about Fred Whipple, an idea Fred Whipple had told me about of collecting cosmic dust with a balloon. The Echo balloons had been flown by NASA, and the population had fun watching them orbit overhead. And they started off working on that, and that's why I put balloon in my original title. But then Kurt Marty showed me a paper, and in fact, by the time they put that project aside and eventually worked on trying to collect the solar wind and using a magnetic field to actually exclude cosmic dust from the collected area, or to move the solar wind particles away from where contamination would occur by cosmic dust. But I tried to explain when Lal told me he wanted to work with Libby that he really shouldn't, because Libby was just full of crazy ideas, and that he wasn't really a very nice guy either. But here I listed some of the ideas that were very prominent in Libby's discussions at that time. He published a paper showing that the Tunguska object was based on 14 carbon in samples, that it was 50% antimatter, which I think most of us would say then it must not have had any antimatter. But that was the paper in Nature implied that, and that there was life on high mountains at the poles of Venus, and he'd tell lots of people that he was going to grow at UCLA diamonds the size of grapefruit by condensation. But I couldn't discourage Lal, and he went through this year. And they published this paper here on their experiments. He did work in the lab of Wetherill, and a little bit, I got an acknowledgement. Ian Kaplan, who's here, got an acknowledgement. He was working in various people's labs, but I played no other role than that in this. They were, Lal and Aruna were at UCLA again, 83, 84. And again, I didn't collaborate closely with Lal, so I don't have any stories to tell about collaborations in those days. My wife in that year became very close to Aruna, and for years would say Aruna was her best friend. Until, in fact, Aruna's early death in '93. And as others have said, Lal was in no small part Lal because of the support he received from Aruna. I don't know. I don't know how long I've talked. Do I have another 5 minutes or so? Or? Yeah, okay, good. So I'm going to end by telling about how in the last 10 years or so my research has sort of folded around and intersected with Lal's again, in particular because of the importance of beryllium-10 in tektites. And so I've got 4 or so slides on this. Tin beryllium is made in the atmosphere by cosmic rays. And beryllium is a very reactive element, and after it rains out, it sticks to soils and doesn't go anywhere. So basically, it stays where it lands. It doesn't go deeper. Of course, some fraction gets washed into rivers, but it's apparently attached to particles when it gets into rivers. That's my understanding. And there's essentially no tin beryllium in bedrock. And the Australasian tektites are the youngest field of tektites. They were formed something like 0.79 mega years ago. And when they were studied by Ma, Herzog, and others, with me being one of the others, it was found that every single tektite from the Australasian field contained beryllium-tin, and contained beryllium-tin essentially at soil levels. I mean, within a factor of 2 of being at soil levels. And let's see what the next slide says. Oh, it just shows you that tektites fall into 2 categories. All of you know this kind. You may not all know that kind. So these are the ones that you can buy at gift shops and so forth. They're formed by molten melt spinning and producing these spin forms. They're called splash forms, but spin form would be much better. But the layered tektites are more abundant. And here you can see the layering. There's a recumbent fold here. And they're all fragments. There is no such thing as an intact layered tektite. They're fragments. So in Southeast Asia, my guess is that there's much more volume of these than there is of these. This is just sort of fun story for you, but we did measure beryllium-tin in both kinds. You'll see them plotted on the next diagram. Oh, well, these form by spinning. As far as I can tell, these form by downslope flow. And in fact, the recumbent folds, I think, form when melt is flowing down, and then the upper layers start to run away and fold up. So I think that's what we're seeing there. Here are the data of Ma et al. On the left, and you can see that the beryllium-tin levels are averaging around 120 times 10 to the 6 atoms per gram. And what does this require? Well, now I need to step back and say, until this work, everybody had said tektites formed by craters. I mean, initially, John O'Keefe, 40 years earlier, had said they formed on the moon, but then we went to the moon and brought back material, and we could see that they had very different compositions. In fact, the bulk compositions of tektites are the same as average soils. Just soil-like composition, soil, shale. And so the fact that they all have beryllium-tin requires that you have to form tektites from soils. You have to form them from materials that were probably within about 50 centimeters of the surface. And my best guess is that they formed during a glacial period. There was a glaciation at about this time that I mentioned, 0.79 mega years, and that they probably formed from something like loess. You need dry, you need fine material. But Lal and his student Gu had investigated loess. So the upper dots here are paleosols, which means sort of weathered loess, at least in this location, which had existed for a long time. And they got higher beryllium-tin contents, but the dark dots are the actual loess samples. And you can see that the values are running around 200, 250. So of the order of twice the values here. But then here's more work by Lal. This is the cosmic ray production of anything, of nuclides as affected by the Earth's magnetic field. So that there's a peak at about 40, and there may be more to this that I'm not remembering, but anyhow, it peaks about 40 degrees, and where the tektites were formed is about 15.5 degrees. And you can see that there's a drop of a factor of 2 here, so that the soils that were on the ground when size form were not very different from this. So therefore, crater tektites are not crater ejecta. Craters form melts over a wide variety of depths, but down to at least 0.1 times the diameter of the crater, and thus even Czech tektites, which are claimed to be from the 24-kilometer Ries crater in Germany, really don't fit that categorization. By the way, the half-life of beryllium-10 is 1.5 million years. The Czech tektites formed about 15 million years ago, but 2 or 3 of them have been measured by this team, and they contain beryllium-10. I mean, there are no reports of attempts to measure 10 beryllium in these Czech tektites which failed. So the generalization based on the evidence we have is that every tektite has soil levels of beryllium-10. So there's no way that you can make a crater like this and then you only produce melt that leaves the crater for the upper 50 centimeters. My preferred model is that, maybe I'll skip this and just go on to the next model, is that it was an airburst, Tunguska-like airburst. And that, so that, like Chelyabinsk, but 10 to the 5th times larger, and that it was, they were melded by radiation from the sky. Thank you.
I worked with Lal a lot over the last 25 years or so, maybe up to 30 years. And I first met him sometime in the early 1980s when he came to Arizona because he figured out there was an accelerator mass spectrometer there and that maybe he could use it for something. And so I wanted to show this quotation that I found in the Times of India about Lal. And I really liked the first sentence about his rugged looks, marine-type suspenders, crimson tie, and Indiana Jones-like character, which when I read it, I just laughed. But this was actually published in the Times of India, so it must be true. So I worked with Lal very closely on, we tried to do radiocarbon and other isotopes and various things. He was interested in doing it in ice. So we published a paper in about 1989, which was radiocarbon in ice, and we moved on from there. So, as many other people have already mentioned, he had many loves, and he was intrigued particularly by anything beautiful, particularly female ones, and also any kind of toys or tricks, or as Jerry Wasserberg mentioned, puzzles, and he would pull out these things. And he would acquire the most amazing little toys, like things that made noises that sound like cows and things like that. This is not planned, but as some people also mentioned, in some respects, he's sort of seen as a god. And this is the previous speaker worshiping at the god. I did not plan this. I didn't know John was going to speak before me. But so there's always a kind of dynamic between the godlike aspects and then the very much more human aspects that particularly Chakraborty mentioned earlier. And of course, we also have to occasionally seek guidance, and Lal and I would have many conversations about these types of things. And we had a radiocarbon meeting in Jerusalem in 2000. These are actually 4, this guy Clowder works in the National Institute of Science and Technology, but Lal actually went to the radiocarbon meeting in Jerusalem, and he was really confused by the tension in the Middle East. He couldn't understand the Middle East. And then he asked me a lot of questions about it, and I said, well, you know, all these people worship the same God, but they have different views about it. And he, first of all, couldn't understand why one would only worship one God, and secondly, why, if they all worship the same God, they would have any kind of dispute. But in any case, that's what he did. So since I worked with Lal a lot, we wrote a number of papers. We also wrote a number of proposals, and so I thought I'd shine a little light on how Lal's proposals were reviewed. Hopefully there were no reviewers in the audience here. It's possible. So this is a comment on a proposal which I should emphasize was not funded. And this is the first reviewer's comments. And the second reviewer, I left out one review that said something like, Lal's proposals aren't the sharpest in the block, or something like that. But anyway, it said something about left gaps in reasoning and so on. And one of the other comments I read was something like that we didn't deal with the question of intrinsic merit, or something like, you know how you have to write all these things in proposals. And obviously to Lal, this was just a stupid idea, because if you wrote the proposal, clearly the intrinsic merit was obvious. But in any case, yeah, this is the one that says Lal is not the slickest proposal writer. Anyway, however, it should be funded. It's still not funded. But anyway, so I have some pictures of Lal, and I show one scientific thing at the end, which leads on from the previous talk. Actually, again, I didn't organize that. So this is a picture of Lal with Elisabetta Boretto, who's speaking later. This is in Candace's house. This is Dick Pugh, who's a meteorite expert. And this is a picture taken of Lal in the Meteorological Society meeting in Tucson in 2007. I think it's a nice picture of Lal. And this is actually a model of the Tucson meteorite in ice. So, as many people have mentioned, he's a very sociable person, a very complex personality, and you could get different aspects of the personality. So you've heard many of these types of comments already. This is Lal meeting with some worthies. This is Goswami, Alan Rubin, Freely. This is Monica Grady. These are meteorite people mostly, in Tucson at an Indian restaurant. And so he was, in this case, in his element. You can see him enjoying the dialogue with different people. He also once went to a Goldschmidt conference in Vancouver, and since I grew up in Vancouver, my family lives there, and Lal became bored with this meeting. So he said, you know, I'd like to do something different. So I said, I'm going to meet my mother for lunch. That's what I said, because my mother's living there, and he said he wanted to come along, which he did. And my mother's older than Lal, and still in very good form, and so they had this conversation that went on for several hours about everything. And this is a bright summer's day. This was Lal being Lal when he's in a very good mood and he doesn't want to talk about science. So I just thought I'd show that picture because it's a little different. And this is of course, this is in Vancouver. So my mother wanted to go to some restaurant that she likes, which is some sort of British-style pub. And of course, when Lal went in there, the first thing he did was inform the people that he's a vegetarian. And of course, British pubs are not known for their vegetarian cuisine. So they had to think about it. Anyway, so I'd like to show a couple of minor science examples. And again, these lead on from the previous speaker. So Lal became interested in, obviously, Lal and Peters shows you the C14 on the Earth. He became interested in C14 in ice, and he was always interested in C14 in extraterrestrial samples. And at some point, we decided to work on lunar samples, and I already had some lunar samples we were trying to look for solar cosmic ray effects and also solar wind effects in lunar soils. And so Lal said, you know, I used to be a lunar PI in 1970. Maybe I can get this reestablished. And so he actually called NASA and said, you know, I was a lunar PI way back in the beginning, and I'd like to get some lunar samples. And they said, yes, sir, right away, or something like that, something that you really can't imagine NASA saying. And they sent him the lunar samples. And I think they may still be in his office, actually, but you might want to check. I don't believe they're in the official, this is something UCSD might want to check out. Anyway, so we did some work on solar cosmic ray effects. We looked at the enhancement of carbon-14 in the very surface from solar cosmic rays, so a couple of centimeters. And also we tried to look at solar wind effects, that is implantation by C14 directly from the solar wind. This was an idea that had previously been put out by Ed Fireman sometime before, and we basically confirmed his general conclusions. The numbers were slightly different, but the conclusions were the same. So the final thing I have is a Lal-type experiment. And so Lal decided that we'd like to look at C14 and other nuclides in cosmic dust, so leading on from John Watson's talk again. The organizers must have planned this. But anyway, so he said, I'd like to study cosmic dust from ice. And we'd actually extracted C14 and other nuclides in ice, and we'd found that occasionally the ice would have a little cosmic grain in it. I mean, you know, just fallen into the ice when it formed, and then the radionuclide measurements would be totally crazy because you had this little bit of cosmic dust with tons of nuclide, C14 and beryllium-10 in it, totally screw up the ice measurements. So he decided to think big, as he did. So he collected all these people to work on this from multiple institutions. Of course, there were no funding for this. And he decided to think big, so he went to the South Pole water well, which is this huge thing underneath the South Pole where people melted out the ice, and there's all kinds of stuff in there, some of which is cosmic dust, but not a lot. And so the task was to separate the cosmic dust from all this other stuff, iron oxides and so on, that was in there, and we actually did this. I won't spend a lot of time on that, and we did some sort of complicated separations where Lal devised a small magnet where he waved it over the sample to pull out the more magnetic grains, which worked quite well. And the result, which I'll just show here, was that we produced, we could measure the concentration of several radionuclides in this dust and actually calculate exposure ranges for these dust grains. We could actually separate the dust grains. And they agreed with exposure ranges of maybe 100,000 or 200,000 years, similar to what we would expect from, say, Poynting-Robertson effects, so sweeping of dust out of the solar system, and so on. And so the conclusion was that this worked, but it was a classic Lal experiment in that, you know, you think big and you have a rather difficult task, and anyway, the result was pretty good. So I have to show this because Wally Broker is here. And one of my first encounters with Lal was that I read this book by Broker and Pang. And I don't know if anybody else in the audience has read this book, but it has these complicated experiments in the book where various famous scientists with their names adapted, maybe Jerry Wasserberg has one, propose grandiose experiments, and this is the one proposed by Lyle Devendra, and you can read it for yourself, and I'll stop here because I'm sure other people have similar stories. Thank you.
I want to thank the organizers for arranging this symposium in honor of Devendra Lal, and it's a great opportunity for me to reconnect with many past acquaintances and to celebrate Lal's long life and scientific career. The only sad part is an event Lal would have loved to attend, and it's sad he can't be here. And thinking about what I was going to say today, I was struck, as many of the earlier speakers have been, by the extent to which Lal's work served as a foundation for a whole mass of research that followed. And one of the major themes of Lal's major scientific themes was his use of cosmogenic nuclides to investigate the global system, the terrestrial system, and how it functioned in the past. It's not the first time you've seen this paper. In case you haven't been paying attention, here it is again. But the fact that it keeps appearing today, this is a paper published in 1967, more than 40 years ago. It is still, its shadow, its program is still something that we're working on. And I'm going to follow one small thread of some of the ideas that were in this paper. This box model diagram has also appeared earlier, but the ideas of this paper was cosmogenic nuclides were not just to be used for dating, but the principal aim of isotope work in geophysics is to obtain detailed information on the mass of the reservoirs, the rates at which water, air, particular molecular compounds are transferred from one reservoir to another. This was a very interesting paper to have been written in 1967 because it was almost impossible to do the experiments that Lal proposed there. We did not have the technology yet to make these measurements, and the thread I'm going to follow is how that technology was slowly developed over the following decades. When my first acquaintance with Lal did not relate to terrestrial samples, but to extraterrestrial work, and it was when I came to Jim Arnold's lab in 1967 as a new graduate student. And that was a time when the chemistry department at UCSD was a center for cosmochemical research. It was the home of Jim Arnold, Harold Urey, Stanley Miller, Hans Suess, Kurt Marty, Gunter Lugmar, Lal, and a whole group of other people were there at that time. The focus in Jim Arnold's lab was not on the Earth, but on the Moon and the imminent lunar mission, which were being planned. And although we've been preparing for receiving the lunar samples, I don't think the impact of the responsibility of the work that we had taken on really hit until the Sunday afternoon when the group of us there was sitting in Jim's living room on Poole Street watching the television coverage of the lunar samples. And I think all of a sudden we realized, oh my God, they're actually going to be in the lab and we better be ready for them. Jim had brought together a team of Masataka Honda and Lal, who had quite a bit of success in understanding meteorites using the cosmogenic nuclides, and they were planning to apply those techniques to the lunar samples, but in a much more intense way. At that time, as I said, the method of choice for measuring cosmogenic nuclides was decay counting. The AMS didn't exist yet. And we had a whole bestiary of detectors, each one designed around the particular decay scheme of whatever radionuclide we were trying to measure. This is one I was responsible for the beryllium-10 work, and that's a beta counter. It's a scintillation spectrometer that used a coincidence method developed by Tanaka in Japan. We had good sensitivity for that time, but we were limited by the decay rate of the nuclide. So for the typical concentrations in extraterrestrial materials in the units that were used there were 10 dpm per kilogram. That means we could measure 100 decays. If we could measure 100 decays per week, we could get a 10% number. So you get a 10% number in a week with 10 to the 10th atoms per gram. Data could not be accumulated very rapidly, but one could do some work. And keep that 10 to the 10th atoms in mind. Let's see. The extraterrestrial material, we had good success with the extraterrestrial materials. We measured about a dozen radionuclides, and in spite of the short time span between the arrival of the samples in the lab and the Lunar Science Conference, we presented the Schreldolf work in Houston, and I think that was quite a success, and it followed up to it was the precursor to a whole series of lunar sample works. And at the same time, terrestrial work was continuing in other labs. Jim's lab continued to focus on extraterrestrial material, but Lal's lab and some other labs around the world continued to see what one can do on the Earth. And one of the advantages of beryllium-10 is that it has very low abundance relative to the other stable nuclides. So if you can find a reservoir where you get enough beryllium-10, it's not going to be diluted by beryllium-9. You can actually do the measurements. And this is just one example of a group of papers that Lal's group published on working on beryllium-10 in the terrestrial environment. It was mostly atmospheric beryllium-10 in environments where accumulation rates were very low, like manganese nodules. A lot of work was done with manganese nodules. You could do that with decay counting. And on marine sediments where the accumulation rates were very low. The world changed in 1977 when Rich Muller published this paper, Radioisotope Dating with a Cyclotron. And the key statement in that paper is in the abstract right there. The sensitivity of radioisotope dating is improved by counting atoms rather than decays. So we had to wait for we had a lot of atoms at 10 to the 10th atoms, but they would just go off at their own rate, and we had to be patient. All of a sudden, you could take all those atoms and you could look at them all at once with a mass spectrometer, and that was an immense change. Now, initially, because it was the meteorite people who've been used to looking for these, using these nuclides, they used the new technique to do meteorite work on much smaller samples in much more detail. But the terrestrial work followed shortly. And one of the disadvantages of the accelerator business is you need something like that. Or you did at that time. I mean, now, things have gotten to be much smaller, but you needed a big machine. That's the FN Tandem at Livermore, which has been used for its 25th anniversary, actually, this year, of its use for a number of things, but it has produced a lot of data for the earth sciences. And you can see from the units that became relevant were not the 10 dpm per kilogram, because we weren't measuring decays, but the atom concentration. And we could produce samples, we could measure samples in the accelerator with a ratio of 1 beryllium 10 atom per 10 to the 14th beryllium 9 atom. So the sensitivity went up immensely in that way. And it could be done in 200 micrograms of beryllium. What that means is that instead of something like that 10 to the 10th atom, we only needed 10 to the 6th atoms. And if you're an experimentalist at all, if somebody gave you, all of a sudden said you had 10 times more sensitivity than you had before, a whole new world would open up to you. This wasn't 10 times more sensitivity. This was 1,000 or 10,000 times more sensitivity. And it was just led to an explosion of research, and explosion of we still haven't begun to extract all the information or to have developed all the ideas that this possibility opened up. And Lal, of course, was involved in all this. One of the first papers to suggest the idea that one would look at these cosmic rays that were producing cosmogenic nuclides outside the atmosphere. They were shielded by the Earth's atmosphere and the Earth's magnetic field, as we heard earlier, but they did reach the Earth, and they did produce at low levels some radionuclides. And he and Jim Arnold published a paper in the Indian Academy of Science tracing quartz through the environment, which suggested a number of the problems that one could do by going to a rock on the surface of the Earth or to some sand, taking the quartz out of it, and seeing what one can learn. He suggested the problems that one might investigate with this. And in particular, I mean, again, we're sort of narrowing down from a range of ideas, all of them sort of exploding from some of the ideas that Lal presented. But one of the threads that one can follow is the question of Holocene climate. Beryllium-10 has a half-life of 1.5 million years, so it's ideal for looking at the past few 100,000 years. The past million years, but in the past 100,000 years, it's a very sensitive nuclide. So there are questions that are listed here. What did the glaciation look like? Was it the same in the northern hemisphere and the southern hemisphere? And what climate scenarios could have caused these glaciations? These ideas, these questions, of course, were always interesting, but they've even become more interesting now that we're doing this big experiment with the climate. And we'd like to know, do the models we have now do a good job of explaining what happened in the past? That'll tell us something about what we can do in the future. But we need very good data to do that. We don't need, the climate was doing this sort of over a few 100,000, thousands of years. We need to know precise timing of climate change in order to really constrain the models. And geochronology, as I mentioned, as I suggested, is the key to answering this question. I've showed two of the papers that Lal's published that sort of were background for this, and this paper is also key to the exploitation of cosmogenic nuclides and working on the surface of the Earth. And that's understanding how the production of isotopes like beryllium-10 and others varies over the surface of the globe with latitude, longitude, and altitude. And this paper, which Lal published in '91, is again, there's been progress, but this is still a key brick in the foundation of what we use to understand if we go to South America or if we go to Greenland and measure cosmogenic nuclide concentrations. We'll go back to the fundamental ideas in this paper to understand what it's telling us, what the measurements are telling us about the samples we've picked up. in order to exploit these ideas, we've needed advances in several areas: mapping, laboratory processing, instrument analysis, calibration of production rates. We need to know exactly where we get the samples, exactly what the underlying geological structures are, to make sure we're not sampling two different moraines, even when we think we're sampling one. This is an example of some work that George Denton has been done in mapping in New Zealand. We had to learn how to sample. We like to sample big boulders because we know that once they're in place, they don't move very much. We need to sample the surface of the boulders, and even going to the point of exploding the boulders with little Hilti cartridges, which are gunpowder cartridges that are used to emplace bolts in concrete. You can see the rock sample coming off there after the Hilti cartridge has been ignited. We had to learn how to do the measurements better. We had to learn how to lower backgrounds by doing better chemistry. We had to get better carriers. We had to learn how to make the mass spectrometer more stable. And all these things have come together. And here's some data again from the Lamont lab, from Jörg Schaefer and George Denton and the collaborators there. This is one of the glacial valleys in New Zealand. And it is a very complex glacial geomorphic structure there. And if you look at the ages, it's a little hard to see here, but if you look at the ages, they're very consistent. We're not seeing scatter all over the place. We're picking out individual moraines that are very close proximity, but we're really getting a detailed history of what the glacier is doing. And in fact, what we're finding, which was a surprise to me, because I assumed that the geologic noise in these systems would be so large that at some point we would say, well, this is just this Mother Nature has said, stop, you can't do any better than that. This is some ages from a boulder field in New Zealand. There are 7 measurements there. The analytical uncertainty, the uncertainty in those ages is 2%. That's the analytical uncertainty. It means if we could do better than that analytically, we could begin to tease apart geologic processes that might be acting. So this is a goad. This is a goad for us to be able to produce even better measurements. So we're not really at the limit. We have to work harder to be able to exploit this technique as well as we can. In addition to being able to do more precise measurements, we're also working on being able to have higher sensitivity, measure smaller numbers of nuclei, so we can look at the effects of inheritance, snow cover, spalling, and erosion. We've actually started looking at historical moraines. Here's 3 dates from a 150-year-old moraine. And we're getting, with Brilliant Pen, we're getting reasonable ages from samples as young as 150 years. The bottom line is that the detection limit is now a few hundred atoms per gram, so a few thousand atoms we can begin to measure. And I think this is the message maybe that we've always gotten from Lal, is that we must always continue to push the limits. High sensitivity measurements will allow us to constrain the range of geologic variance and extract the maximum information from paleo records. And actually, it's just it's sort of a mantra for whatever we're doing. Just don't give up and keep pushing. Thank you.
All right, so our last speaker before lunch is Marek Sreda, who's going to talk about water and cosmic rays.
Thank you. Good morning, everybody. This line of work was inspired by Lal's work on cosmic ray neutrons, and it all started with when I was a grad student, and I did what Bob Finkel just described, cosmogenic dating of glacial deposits. And we discovered that some of these isotopes, and particularly chlorine-36, are sensitive to environmental water. And this was a problem, but also a new idea. And the new idea was that why not measure neutrons and infer water content in the environment today? So that's what I'm going to talk about. So why is water important? Well, this is just one example of feedbacks between the atmospheric processes and land surface. In this case, it's feedback between soil moisture and precipitation. In some places, about 85% of precipitation comes from recycled soil moisture. So if we understand soil moisture, we can predict weather, predict precipitation, and we can just improve our forecasting skills. But soil moisture is not easy to measure. There are two reasons for this. One, huge spatial variability in soil moisture. These are just two examples, and this is common. If you go to a place that is, let's say, 200 meters in diameter, and you take 10 samples, they will be completely different. Typically, we take one sample for weather forecasting. The second reason is that our existing methods are point measurements or huge vastness of satellite pixels, 40 kilometers by 40 kilometers. Neither of them is useful for meteorological applications. So what we need is something that is intermediate in scale, and this something turned out to be cosmic ray neutrons, and particularly one type of cosmic ray neutrons, fast neutrons that are generated by secondary neutrons that Bob Reed and others described. They are generated in the atmosphere and also in the crust, and then they are moderated. And the most important moderating element is hydrogen, and specifically the proton that sits at the center of hydrogen atom. So if we can measure neutrons, fast neutrons, above the land surface, we can infer moisture at the scale of about 1 kilometer. And this is nothing new. I thought that I invented something very new and very cool, and then I found the paper by Hendrick and Edge from 1966, in which they showed that this is the case. The neutron intensity above water is about a factor of 10 lower than the neutron intensity above ground, dry ground. And this is basically what we use, the difference between the two cases. We are somewhere between the two lines. I think I can skip this. This shows the same cascade that Bob Reed showed. We start with protons, primary protons, then we generate the cascade of secondary neutrons, and then we generate evaporation neutrons or tertiary neutrons that are then moderated on hydrogen. And here you can see how important hydrogen is for moderating these neutrons. If you have no hydrogen, no water in rocks, this is the top panel on the left side, oxygen is the main moderating element. When you have 1% of water in soil, hydrogen constitutes about 50 to 60% of all moderation. It's more than all the other elements combined. And a typical soil moisture contents of 5, 10, 20%, hydrogen is the one that matters and nothing else does. Okay, on the right side, the top panel on the right side is basically the summary of the left panels, and the bottom on the right side is the calibration function, the relationship between neutron intensity and water content. I will skip that. How is this measured? This is we measure neutrons with proportional counters, and these are the same type of instruments that Lal used in the 1950s, also to produce some of the data for his PhD thesis in 1958. It's a tube filled with helium-3 gas. When a thermal neutron enters the tube, it produces an avalanche of electrons that are deposited on the center wire, and then they form a pulse that we can shape, amplify, and count. And basically we count TTL pulses. In the field, the instrument sits on a pole 1 or 2 meters above the ground, and it samples the well-mixed reservoir of neutrons. It's much like a thermometer measuring the temperature of the air. It measures the average kinetic energy of the particles, and we do the same with the neutron detector. We measure the density of neutrons in the well-mixed reservoir. And the mixing is at the scale of about 700 meters in the horizontal, and it extends into the air about another 350, 400 meters. So it's a hemisphere. Everything that is inside the hemisphere will be reflected in the cosmic ray neutron intensity signal. Anything that is within the footprint which means farms, roads, trees, meadows, rivers, all this and more. And we learned how to disentangle the total signal. We can isolate a specific component, and in our case, the most interesting thing is soil moisture. But we can also measure water in biomass, water in snowpack, snow water equivalent, and any other water in the environment. Of course, every new technique needs to be validated. This plot shows 9 or 10 validation data points. Each red point is about 100 soil samples that we collected in the field, and we compared with the neutron-derived soil moisture. You can see that they compare very well. The average deviation is about 1%, which is very good. So it gave us confidence that this is something that is working pretty well. I will skip snow and stop for a moment on the vegetation slide. We can measure the amount of biomass at the scale of about 700 meters because trees and other vegetation, it's mostly water. It's like 60%, 50, 60% water. So if we have more trees in the environment, in the footprint, then we will have lower neutron intensity. And we did a controlled experiment in the forest and in the burned forest, just a couple of kilometers away. And surely you can see that the wildfire neutron intensity is higher than the pine forest neutron intensity. In the pine forest, we have hydrogen in the trees that sucks out neutrons from the environment. So from the difference, we can compute the amount of biomass. And this is something that is unprecedented in ecological sciences. Usually what people do is they go out and measure 2,000 or 5,000 trees, the diameter and the height, and they compute the biomass. So here we can do this with cosmic ray neutrons. Something that I'm doing, or I was doing with Lal here at Scripps, at the Scripps Pier, we noticed that there is a persistent diurnal signal in the neutron intensity, and it's not, it cannot be explained by the normal neutron intensity variations. So we were doing some experiments on the pier and also inland from Scripps just to see what causes these diurnal fluctuations. And now I asked Ray to allow me to continue this experiment. So we will be setting up another set of detectors at the pier probably tomorrow. I will skip this and go to the last part. We developed this method for measuring soil moisture, and we are now implementing it in the global network of cosmic ray probes. The system is very simple. It has neutron probes called neutron AFCA here, a neutron monitor, which monitors the high energy neutrons that follow the 11-year cycle, solar cycle, and a bunch of servers at the University of Arizona. And we have satellite transmission to the Iridium satellite system, which is not depicted well in this figure. These are not Iridium satellites. This is Sputnik, that's right. So we started the system in the United States with about 60 probes. I will skip the server, but you can get the data online. And I would like to stop here at the global cosmos. So we are installing this network in the United States with the goal of about 500 probes in the next 5 years. Other countries picked up. So we now have what we call the global cosmos of about 120 probes. Another 120 or 250 are coming with funded proposals, and a bunch of proposals are under review. So this is really a global thing, and if you could consider the University of Arizona to be the father of this system, Lal is definitely the grandfather. We couldn't have done this without his inspiration. Thank you.